Okay, I think we can start. It's 10 after the time we said we would start. Thank you, Darwin, for accepting to make a presentation in this workshop. Welcome everyone to the workshop. Darwin is going to talk to us about relating the fundamental research on cable-driven robots to the practical developments that he's doing over there in Hong Kong. So go ahead, Darwin.
Great. Okay. So yes. So thank you, Philip, and also Hamid for the invitation for today. So yeah. So there's a lot of talks on cable-driven robots today. Obviously, that's the theme, and I guess I'm the first one due to time zone. But I also get the advantage of speaking whatever I want, and nothing is going to be it will just be a repeat if it's coincidental, right? So so let's start. So okay. So I'd like to talk today really about the fundamental work that we're doing and how that leads to practical development. I think that's a question we're all thinking about these days, is how do we bring cable robots to the real world and what's missing in order to do so. So to talk about the stuff, some of the concepts of this, I'll first introduce CDPRs, as that should be fairly standard. Talk about the practical applications first, just to motivate the challenges that we're facing, that we're doing. So it's not really about what we've done, but what we're not doing or hard to do. And then the modeling analysis, development in fundamentals and software development really try to address those sort of issues that we're talking about. So I think parallel robots and cable robots should be familiar to those actually in the presentation today, since that's the theme of the talk. But nonetheless, I'd first talk about it. It's basically working, instead of having robot arms in serial, we have robots with multiple linkages in parallel, and cable-driven robots is extension of that, where cables are in parallel. And then the unique challenges involved, the two that I will focus a lot on today. One are the constraints in cable force, because it must be positive. The second is the actuation redundancy, especially for fully constrained systems that result from cable-driven robots. So the advantages also should be well known. I'll just quickly go through it. It's typically lightweight in nature, capable of being large in nature, easy to transport and reconfigure the system, and also bio-inspired for those people who are interested in that aspect of cable robots. Now, some of the things I observed in CDPR work over the years, I guess, one is, I like this type of robot. I've been doing it for many years and it's interesting, but a very niche type of robot, I would say. So the community is not massive, but lots of interesting problems involved. The question is, why is it so niche and why cannot be mainstream? And part of it is also, when used right, it's extremely suitable. But I certainly, I think, we don't want to fall in the mistake of trying to put cable robots everywhere, even when it's not suitable. And of course, a lot of groups are working on different problems. Are we scattered? Are we working together? How much working together? How unified is our work? That's an interesting question to explore. And also, I think cable robots are starting to be out there, but still there are many opportunities available, but it's starting to be out there. I don't know how other speakers will feel, but I think we're only in the beginnings, and even then, probably quite early in the beginnings. So the work we do in the COHK in Hong Kong, so Chinese University of Hong Kong, is we work on a range of aspects of cable robots. So we feel like the things are all interconnected between fundamental work, like the control, analysis, dynamics, kinematics, to developing software and hardware so that the systems can go in the real world. So for myself, the applications that I target are mainly related to either bio-inspired systems like humans, in architecture, so large-scale construction works, and also service and maintenance. And all of these actually are quite widespread. So rather than a particular type of cable robot I work on, I tend to work on a range, a family of cable robots. So one of the important works that is close to my heart is the generalization of cable-driven robots. How do we not just develop a technique for a certain class of robots, but try to generalize that over the many types, because we need it as a combination to work in different applications. So first topic I'd like to go through is some of the real-world projects that we do, just to briefly introduce the motivation behind it. One of the ones that we've been working quite a lot on, as you see from 2017 till now, is constructing brick structures using cable robots. And that's a no-brainer solution at the time, as a no-brainer idea to work on, because you get large space. I could move in large space, easy to set up, suitable for real site work, and the payload would be more than suitable to do so. So in this project, we started with a range of demos because that's where the state of the robot was. Had demo it just for a short time, maybe a day, maybe 2 days. How to run that over a month? How to run that over? Recently in a Hong Kong Science Museum, where it's for the public, we've been running it for nearly a year. Okay, and basically it's running on a daily basis. Of course, we need to maintain it, but still, it's running very, regularly. So it's, I would say, rather than a prototype, it's really a display now. So, but then it's not. How do we move that to real world? So, just want to introduce. This is the system that we've got at the Science Museum. So basically, this is the cable robot. It's about 4 meters by 4 meters by 2 meters high. It's sort of an autonomous delivery system, since I cannot infinitely construct bricks and with glue, because I need to dispose of it. It's running every day, I don't know, from 10 a.m. to 7 p.m. And then the public has a button. If they like to see it, they press a button, then it runs a sequence or two, and then it picks up bricks, and it also cleans up the brick itself. So it's also a reconfiguring cable robot. So the sliders that actually make the cable robot go up and down the bottom cables to avoid interference with the bricks. And of course, as we all know, we're able to achieve a decent accuracy with cable robots these days, depending on the cable you choose, etc. This is the time lapse of the building setup. The person is going in and out because we have to feed the bricks to the feeder. The feeder system cannot tackle hundreds, thousands of bricks. So we manually load it. In real site work, there will be work there, right? This is the sort of setup there in the Science Museum. The real work that we're moving towards is a real site construction work that we're doing. We've been preparing for a long time. It's again a reconfiguring cable robot with sliders at the bottom, but larger scale now. It's about 10 meters by 10 meters. And we're doing the prep work. Hopefully soon we will have the real site operation video to show everyone. So in that sort of project, we will, aside from the development on the front end, the actual robot development, we also need to work on a range of fundamental supporting. I'll talk about the different fundamental work we do in that appropriate section. So another robot we're working on is placing cable robots on facades. So rather than having humans on gondolas, a natural extension is to have cable robots on facades. So that's another sort of larger scale cable robot type of situation. That makes sense because gondolas are also cable driven in some ways. So the idea is, by having a cable robot with a robot manipulator on top, we could do dexterous motion at the same time as gross motion. And of course, aside from the engineering development, the key challenges here would be the control of this sort of relatively redundant system between the cable robot and the robot arm. So I'll talk about that later on as well. So we use that for window cleaning. So we use the force sensor on the robot arm to maintain manipulation contact. And we need to do that later when we're on the cable robot platform as well, and how to maintain the cable robot platform to be stable. We also do the same thing with painting. Okay. Another thing that we're also interested in is to teleoperate this system. So right now you see a video on where there's no cable robot, but actually we're also developing algorithms to do teleoperation with the cable robot on top. And we'll talk about that as well in the fundamental work. So we're doing a site setup right now. All the parts are starting to be shipped in from all sorts of places, and we want to assemble this sort of setup about 20 meters tall. We of course, behind it, there's also workspace analysis to make sure we choose the right motors, because we only have one shot at doing this, I guess, given the money and the time effort to invest. We need to get the right actuators, the right setup for the proper purpose. So another one is the cleaning of a sedimentation tank. So this is a robot that developed, supported by the government, and they want to use this to clean the sewage tanks, which is extremely unwelcoming for human cleaning, obviously, because it's all sewage water. So we developed a cable robot on a fairly, I'd say, massive frame. So the frame is about 9 meters off the ground. And then we placed a cable robot, a fully constrained 8-cable cable robot in there. We need to move it from a prototype into something more mature. It could be out in the open, rain, thunderstorms, typhoons. It was there. We set up that the cable robot was about there for like 8 months to a year. So it withstood all of those annoying issues of weather. We needed software to make it relatively easy to control. And it would move and do automatic cleaning, basically holding a brush and scraping the boards, I would say. Okay, so that's sort of the setup. This is a close-up of how we mount a manipulator, an end tool to do the cleaning. We also tried high pressure jet, so the stiffness of the K robot is quite good. So even with a pressure jet, it's able to counter the reaction force according to that, and then you get the idea. You can move in the whole space where humans cannot really go to either. Okay, so we developed. That's the application we developed for. Went through multiple stages of cable robots. So that's going from the lab to a site setup to something more mature. That's the journey of cable robot development on a real site. Scaling up, scaling in seriousness, scaling in time. That's what we're doing. So the frame was fairly heavy duty, just to avoid having too much deflection. So we did the full analysis on the frame deflection as a result of the cable robot to minimize that. So not only is it safe for the frame, but also the kinematics of the robot. It was a dual spool setup with a brake, mechanical brake. So when the system was off, actually the brake would engage to hold the robot in position. So every day, because day in, day out, we need to operate this cable robot. To do that, again, a bit of analysis to make sure what we're doing is reasonable, the cable forces in the system. Develop different tools for that purpose. I won't talk much about that here. Another one that is worth talking about is the calibration. So it was super annoying. You got to calibrate all the cable attachment points. For an assembly this big, you're never ever going to get the attachment points anywhere accurate to where you plan. So you needed to actually use systems, whether it's algorithms based on self-calibration or manual using lasers. You need to do something to calibrate the system. Then you need to go through from the GUI to generate trajectories, inverse kinematics, the robot. We need to go through that for the system to operate. So now, okay, a few topics quickly to go through about the fundamentals. So the first one is modeling. So, as we said before, the type of robots that we work on is quite widespread. So we're talking about a range of different robots, not one particular type. So in that case, we needed to be able to model and analyze all type of robots. Now, of course, typically we could model each robot individually. I could write the Jacobian, I could write the analytical dynamics, analytical kinematics per robot. That would be fine if I'm only working on one or two type of robots. But if I'm working on all these type of robots and I did it one by one, either myself or my students would get very frustrated. So as a result, we wanted to develop a generalized model to study this and a generalized analysis method for these things. So we wanted to unify all of these work in a common framework. I think that's sort of the theme of that we do of a lot of the work in our lab, from the modeling analysis to even the software and even the hardware setups. We're generalizing it so that it works on multiple setups rather than an individual setup. So we're talking about, there's so many different types of cable robots out there: spatial robots, multi-link robots. Within spatial robots, you've got fully constrained, under constrained, even under actuated. You've got multi-link robots where you've got a single segment of routing, just cable to one point, or cable to multiple links and multi-segment. But all of that, really, there's common things behind it. You have a common body model, as long as you model all this in a generic manner. All of them will have common mass and inertia type of properties that govern the dynamics of the system and the joints. On the other hand, unique to cable robots, you have all of the cable models and actuator models. You can have cables, and we're even exploring thrusters. You could have unilaterals, you can have springs, you can have variable stiffness devices. How do you model all of that generically? That's sort of what we've classified. So there's a few problems that we've been looking at, how to model the routing generically. We developed a range of different matrices that will allow for the configuration of the robot to be represented generically. So when you have for example, these ones talk about how the base point and the end point are attached. If I've got two segments, then I've got two rows. If I've got three segments, I've got three rows. And these represent how the multiple links translate. And if I've got an unknown cable robot, I could just model it generically. Then when I want to actually do my analysis and do my execution of my code, I could just substitute the numbers inside. And this is a generic way of dealing with it in general. You could also have different types of actuators. As I said, you could have spring, ideal massless cables. You can have spring cables, variable stiffness. We even mimicked the human-like muscle model. These days, I haven't got it in the PPT, but I've also added thrusters, UAV thrusters. So they have their own dynamics and their own model inside it. And we want to model all of that. And you've also got a range of attachment points. You've got point attachment points for lightweight robots. And for heavier weight robots, you've got these rotating pulleys. And then all of them have common properties. And as long as we identify which are the common properties, develop a single model for them, then I could write one piece of code that would work on all type of robots. So the last one would be the type of robot. So you have spatial, you have planar, you have, revolute joint, spherical joint. You could model all of them, and you could even have them partially actuated. So if I have a cable robot with a robot arm on top, I could have actuated joints and unactuated joints in combination. And again, then you could have a generic setup. So we'll talk about those sort of things more later as well in the analysis. So then in the fundamental analysis, so I've picked a few. There's been different work we obviously do with all the students we have, but I picked a few that I think are interesting, or at least have some concepts that I want to share with everyone and to think about, some cables for thought. So the first one is workspace analysis. So a lot of work we've been doing recently is on a type of workspace analysis called ray-based workspace analysis. So I like to talk about that. That's very different to the typical types of workspace analysis in the past. Now, but why is workspace analysis important? As some of us may know, is it's important because there's lots of constraints in cable robots. You have force constraints and you have collisions. And by doing that, then you could understand how cable robots work. You could design cable robots based on its workspace, and that's what we do. You could also control cable robots actually using the workspace. That's also one thing that I think is quite novel that I want to share later, how we use workspace analysis in order to develop controllers. So let's summarize some of the type of existing workspace analysis techniques that you may be familiar with. First one is analytical. So again, I want to highlight none of these are good or bad. It's not that certain type of analysis techniques are not good. It's just that they have different pros and cons. So for workspace analytical workspace analysis, you get an exact solution. You get very fast generation of the workspace. But there are some drawbacks. Not all workspaces have analytical forms that are easy to use and manipulate, and may be difficult to analyze. I calculate the workspace boundary. How does that help me to calculate other properties? Can I use it? Is it as helpful? Also, it's hard to generalize it. As I said, I want to deal with all types of cable robots, so I want something more generic. So the natural, more generic approach is pointwise. Another classic. Instead of evaluating an analytical boundary, let's check a binary condition. Is this point in or out of my workspace? If it's in, it's in. If it's out, then we put it as negative. Advantage, very simple study, very simple to generalize. This is, we could claim, works on all type of cable robot morphology and topologies. But of course, there is its own drawbacks. There's no continuity between points. So if there happens to be a singularity boundary inside it, you may miss it and you can't see it. Second, it's sampling, which, in general, people don't like sampling. And also, it's slow to generate. It generates workspaces in the scope of hours, right? There's also interval analysis, which has it's a great extension, great a balance between the analytical and pointwise, because you've got continuity information. You get a guarantee rather than just a point guarantee. You get a volume guarantee, the internal, all this. It's also, I wouldn't say it's fast by any means. And I would say it's difficult to generalize to different classes of systems as well. So that's why we're interested in ray-based. It tries to combine. I think I would pitch it as it's a middle ground between pointwise and interval. Basically, rather than treating a single point, rather than treating a single box, let's treat it as a line instead. And when you do that, it's actually, you get some continuity information. So not all, but some. So I should probably put in brackets, some continuity. I'd say it's very fast to generate. In fact, it's faster than pointwise as well. So you might say, would it be in between? It's actually faster. We could generalize it, but of course, it's still a sampling approach. So it's still not perfect, but it's a middle ground. So obviously I like that because we've done quite a lot of work on that in recent years. So let's talk about a few examples of what it basically means. Wrench closure analysis is a common one. It represents a condition in which the cable robot can generate wrenches in any direction, in arbitrary magnitude if I have infinite cable force. So what we do there is we actually take it as, we do the analysis by looking at the row reduced echelon form of the cable robot, of the Jacobian, which is common. Then the condition is, as long as the last column is all negative, then the cable robot is within range closure workspace. So that's a very well-known condition prior to our work. But what we found that was interesting was if you took 1 degree of freedom, whether it's a translation or an orientation degree of freedom, as long as you're dealing with 1 degree of freedom at one point in time, actually all those equations become polynomial, univariate polynomial. So you could actually solve that using classic solvers. So that is a convenience of the ray-based approach rather than using workspace conditions like ray-based or point-wise, we have to check binary conditions. We actually could solve for the analytical boundaries, just like the analytical approach, but in 1D, but more efficiently because it's only univariate polynomials. The other condition we also worked on is cable-cable interference, and we found this one is more common that we know because it's very similar, right? You have a manifold boundary that you know the multivariate closed form expression for, and as long as it's 1 dimension, again, it's a polynomial expression. That is relatively well known. So we also do a similar thing where we take the analytical conditions, check for it, and found that in a univariate case, a single dimension case, you could get the boundaries accurately rather than sampling point by point. Just directly get the boundaries, then the ray in between is in the workspace, and you have a placement of that. The other thing that we started to look at was also cable and obstacle interference. And one thing that we've used the property of is the fact that there's a sweeping when you do a ray. When the cable robot moves in 1 dimension, if it's translation, the cable itself will form a triangular plane. If it's rotating, it will form a cone. And a plane is a degree 1 equation. A cone is a degree 2 equation. Once we combine that with the polynomial forms of surfaces, we could actually get a whole range of polynomial solutions of various degrees. So you see here, we check the intersection of between a plane and a cone with degree 4 surfaces up to degree 4. So when it's linear, it's planes. So you could do polyhedrals. Quadratic, you have cylinders and spheres. Degree 3 is not that useful, actually. So degree 4, you get Gossets, you perform toruses, all sorts of shape. And then we combine that with the interference of the sweep to calculate the closed form boundaries on when the sweep intersects, and you get a array solution, again, polynomial. So then we did that, and then this is the results. It works on both translation and rotation. It works on a range of obstacles as well, and it's very efficient. So we compared also works on multi-link, so it's also generic for any type of robot. It works it's faster computation compared to point-wise by a reasonable margin, and it's relatively fast even for different type of surfaces. So different type of shapes and geometry you can use ray-based approach for. We then also extended this ray-based approach for not just straight lines, where you think straight lines are rays that just shoot in 1 direction. You could do curves, because again, as long as the curve is a polynomial, when you do polynomial versus polynomial, you still get polynomial. So we're trying to push the boundary, how much polynomial we can push right here. And then we also use this to do trajectory generation. So rather than using the rays, we could then fit in smooth curves in between and verify that this whole curve is within the workspace. So rather than just simply checking point by point if it's in the workspace, we could actually check it just from start to end in 1 continuous flow. So these are sort of the ray-based workspace stuff we do, and we keep still working on it to try to push the boundaries to get the speed, generalization, and type of workspaces to the next part. So next one I'd like to talk briefly about is control. So control is a very challenging problem and a headache issue because cable robots are naturally nonlinear constraints. You have a non-convex problem. It's computationally inefficient. And also, control is hard because if you don't have good control, you can't have good accuracy. You can't have good accuracy, it does not work in the real world. So really pushing it to the real world, controlling the robot is super important. So we do a range of different controllers, from predictive to iterative control, that will work on a range of different robots, and we'll talk more about that. So first one to talk about is model predictive control. So the basic problem of model predictive control is we have input of the state, the pose, and the velocity of the robot, and the input is your cable force. And this problem, naturally, when you formulate it to minimize tracking error and to also minimize effort, it's non-linear and non-convex because you've got the equation of motion. You also have cable force constraints, and you have other state constraints like collision. So the method we propose is actually called Workspace Model Predictive Control. One may think, how do you combine Workspace and Model Predictive Control together? Actually, we use Workspace to linearize and convexify the controller rather than being a non-linear control. So the way it works is we have a QP solver solving the linear problem, but we use Workspace Analysis to pre-generate some conditions that will convexify this controller. So by knowing the workspace in advance relative to a reference trajectory, I could actually make some convexification. Let's do a simple example. The workspace here is a non-linear, non-convex shape. If I took a reference point here and I find a box around my workspace, then actually this box is convex. So Workspace provides me a region, hopefully a large enough region, that could be convex for my controller. So that's what we did. So we took the problem, we first did feedback linearization to linearize part of the problem. Then you've got a non-convex input constraint, and then we use Workspace. So how do we use it? We used constraints on the velocity and acceleration to generate the wrench feasible workspace. And the wrench feasible workspace will then provide us some poses, the region of poses in which the robot will still be controllable and stable for the controller. And actually now this problem is actually now convex and linearized and actually can be solved using a QP. So we also explain the concept a bit more. You need to first have the input as velocity and acceleration. So if my robot is slower, then I have a larger workspace. If my robot is actually quicker, like 5 seconds, I have a smaller workspace. Then you could design your constraints for your controller based on these parameters. So you see here, we designed the parameters according to the workspace. And then, we show that the control performance was good. And we also ran it on hardware. So we generated for a planar robot, looked at the trajectories and the workspace. It's inside using the workspace, generate the constraints for my controller. And, you're able to track the reference trajectory. That's very good. Another problem on control I'd like to share is operational space. So what this refers to is we typically control the joint angles, degrees of freedom for a robot. Now, for a single link cable robot, the joint space and the operational space are equivalent. They're equivalent things because it's just your end effector pose. Here it's different because your target point could be a different state that is of a lower degree of freedom. So there's a 3-state redundancy: actuating, joint, and operational space. We developed an iterative and reactive control in order to do that. So I'll show a video on what we're doing just to give a better idea for everyone. I apologize. I don't know if my PowerPoint is frozen, and it has. So
Darwin, we have 2 minutes left normally, so if we want to allow for some questions, maybe
I'll just show that last video and I'll wrap up there, I think, right?
Okay, thanks.
Yeah, so let me quickly open up the PPT. Hopefully it doesn't crash again, the video. If it does, then I could wrap up right there, right? So this one. I'll try to show it, here, just so it doesn't crash. So basically, the operational space control, we want to control the position of the end effector while doing a set of constraints, avoiding collision, good manipulability, and dexterity as well. And basically, this is the reactive controller. So we're able to first already get a good performance with the reactive control. So one might say, why do we need the iteration? Well, part of the reason is because when you have a reactive controller, it might do some awkward motion just to prevent bad things to occur. So in this case, to prevent cable collision, you see the tracking performance is sacrificed because you don't want to hit the robot arm doesn't want to hit the environment. So here then, we do a control where over time it repeats. It basically does the motion again and again. And by repeating motions, we learn over time by doing local optimization how to improve performance. So you see here, over time, we repeat this over multiple iterations. And then before and after, we get better dexterity. So the robot found by twisting itself a little bit more, it will get better dexterity to operate. Okay, so then, you know, the error is decreased. And we see the same thing here. After we're doing the the iterative control, it actually preemptively avoids the need to do worse tracking in order not to hit the environment. So that's sort of where we're at with that. So on that note, I'll just wrap up, I would say. So, you know, I think, you know, Cable Robot is an interesting thing that we're working on. And, you know, there are a range of solutions that we're all proposing in order to do that. And I think that's sort of where we're heading towards, trying to make this ready to hit the ground and be used in the real world. So I'll end it here. And yeah, thank you for the time.
Okay, thank you, Darwin. Maybe we have time for one question for Darwin. Anyone? Well, I would have one. Maybe Darwin, can you go back to the comparison between the workspace tracing methods?
Yep.
Is it too far or?
No, it's right here. Yeah. Is it this slide? Let's see. Is it this slide?
Yes. I think your method is great, and I think it's very innovative, the ray tracing method. But I think one other method that's also great is the method that by Andreas, where he uses rays from a single point at the center of the workspace, and it seems to be very quick. Do you see what method I'm talking about?
Yes. The whole generation. Yes.
Yeah. How does that compare to your method? Maybe I missed it. Maybe you mentioned it, but.
Yeah, well, I think it's on the same line. So I would say that method to me is also ray-based. Obviously, the way we solve it is a bit different. I think, as far as I know, I think the way it's solved in Andre's work is to look at bisection methods to find it.
But again, does a regular line search, right?
Yeah, regular line search. But you could actually formulate that same method where you shoot, because, you know, we shoot trajectories as well, right? So you could shoot arbitrarily and still get the closed form solution. So you can certainly do that. So actually, it's very similar in terms of the concept. Implementation is a bit different, and obviously the assumptions on the closed connection is a bit different. So one difference I would say that I just quickly, you know, summarize would be, I think that method you shoot from a center point out. So without having the lattice part, the intersection, it's hard to conclude that the connection in between those parts are connected. So that's probably the difference, right? But yeah.
Yeah, and I guess with the bisection method, you don't guarantee continuity really between the center point and the points on the hull, I guess.
So, yeah, I think that's probably the main difference. But I would say, though, I mean, to be fair, so firstly, you know, the ray-based is not only us doing it. So Andre's work certainly is that the type of method is also ray. I would consider that as ray-based. Yeah, certainly.
Okay. Well, thank you, Darwin, for your great talk and your very diversified research. It's very interesting. Thank you for sharing it with us.
Thank you.
Okay, so now we can move on to Hamid. Hamid, can you share your screen? Yeah, okay, great. So the title of the presentation is Cable Robots Applications in Art, Challenges and Developments. So go ahead, Hamid.
Okay, hello everyone. From good morning to good evening, the diversity of audience we have. Before starting, I would like to thank all the speakers. Tobias and Stefan are also with us. We didn't talk to them before the beginning of the start of the Darwin. What I am talking about today is one specific application of cable robot, which is, in my opinion, different from the others and somehow interesting application in the art. What I will give today is a very short introduction to our group, ARAS. then robotic application in art. The structure that we have used, a bit of some theory on parallelogram links, some analysis, optimizations, and some experimental results. About ARAS, we have in ARAS is the acronym of Advanced Robotic and Automated System, and also is a name of river in Iran. We have different active research group, as you see. One of them is parallel cable robotics, which the result of what is presented here is mainly the work of the group, and I'm only the presenter. On parallel cable robotics, we aim to develop new robotic-based technologies for a variety of industrial and artistic application. Before starting with the artistic application, let me just introduce a number of our products. The Nasir is our first product, which was a 4 fully constrained robot equipped with 4 actuators, a planar robot. What I'm talking about is Kamalul Mulk. Kamalul Mulk is a name of a very famous painter in Iran, and our robot is also named after him. We have also some Delta robots, some other parallel mechanism developed in our group, which I'm not talking about that, and also the ARASCAM, which is a suspended cable robot, which I will introduce it very shortly at the beginning. As you see here, we started our experimental setup on a planar case, and which we call it Nasir. Nasir consists of 4 cable-driven actuators with 3 degrees of freedom, planar motion, which provide a large controllable workspace. This controllable workspace consists of the moving platform poses in which the wrench can be exerted in the moving platform while cables are all in tension. This is what Darwin explained a lot in wrench feasible workspace and the different type of obtaining it. And the special design has been considered on the winches to have the anchor points right at the one single point to have better kinematics. We have developed a lot of control-based experimental cases on this platform. Then we go to suspended and 4 cable driven. We call it like a spider cam. We call it ARASCAM in our lab, which consists of 4 different towers, everything fully developed modular to have more of them. We have 4 sensors, we have the drums and also some transmitters and the cables working on the end effector. And this spider cam is mostly used for large workspace video filming or video capturing. One effective way, or one thing that we would like to maybe emphasize for the community here, we worked on the end effector of the spider cam as well. And we put a lot of different type of measurement units on that. As you see, we have a Bumblebee stereo camera. We have another just monocular camera. We add some IMU bases, NVIDIA Jetson SBC on that for video capturing. This is basically to generate, we call it the data set or the data collection, complete data collection that some other groups can use in deep learning or other vision-based method for localization and also for visual odometry, different type of things that can be done on cable robotic. And the data set that has been provided is maybe the first data set that can be published for the researchers. But going back to the art, robotic has been used somehow in art. We can see that we can use different type of robot for painting, for sculpturing, for wood carving, and or for tiling. We can say that in our group, we are working somehow in these three applications with different type of robot. For the painting robot, we are using cable robots. And as I introduced that the first version of our Camel Molk robot, which is a painter robot, very simple. Camel Molk is the first example of a painter CDPR that has been developed in Aras. This robot is able to draw portraits and calligraphy with various Persian font. And it is very simple. It is deployable. It can be used in many different places. And it is interesting to bring the robotic application into the real life of community. Camel Molk version 1 is a simple suspended with 2 cables and also 1 degree of freedom. I don't say 1 degree, half a degree of freedom just to push the marker on the board or taking it off. So it is a XY plane motion, and it is servo actuated. How we can paint basically a picture. This is a black and white picture at this moment. The first thing is we should get the picture, any image, any image, and then we can change it into SVG stable vector graphics. Then we should produce a desired path. It could be optimal path for the robot to move, to have some different lines on the board. We have a central controller, of course. We have the programming, the software that makes sure that the painting is going to be out. And then we have to draw the picture with excellent quality. Here you will see a painting of a picture of Khaja Nasiruddin Tusi. I just put this picture. Khaja Nasiruddin Tusi has been lived in 1201 to 1274. Is a Persian scientist, philosopher, mathematician, astronomer, theologian, physician, and the most important thing about him is a prolific writer. He has a lot of books. And the university is named after him. So this is the way we can draw a picture like this. And the final art is interesting, but how the art is performing attracts a lot of attention to the audience. This structure, of course, is the first structure, very simple, very low cost, and also it is very deployable, very compact, user-friendly, very low implementation cost, but it is slow. We have, make the movie faster for your view. To draw this picture takes about 10 minutes or 15 minutes. Of course, if there is some time for some people to look at it, it is fine, but we have to increase the speed somehow. And the main difficulty is the suspended case, and we need more attention for that case. This robot has been used in a lot of festivals in Iran and outside Iran, or neighboring country. You can see the Hamid Karzai here. Here it's also another festival in Erbil in Iraq, and also in some festivals in Iran. These people, this is Zarif, I guess other people also can recognize him as some of our PMs. But going toward the challenges and how to solve the challenges, we go toward designing the second version of Camel Molk, which I call it Camel Molk 2. In this second version, we are using parallelogram lengths. The idea was to increase the stiffness and to increase the speed of motion. The idea that is used in many parallel manipulators, like in Delta manipulator or other non-cable driven manipulator, using parallelograms. Of course, this is not the very originated idea from us. Other people have also used parallelograms. I know that Clement and Philip also has been working on that. Different other people has also worked on that. And we are using this and somehow analyzing how it can be beneficial to the application that we have. The idea is very nice, but of course the analysis and the design becomes more complex, and the system is not suspended anymore, and we can have some better idea on that. So very short on some theories here. We define somehow a general way how to connect the cables in a parallel form. We define different shape. We call it I shape or 2I shape. Two drums with two cables which are parallel. We can use two pulleys on the moving platform. Then we call it U shape with one single drum. Here we have a V shape. We can have this not going back toward the same line, going toward another line. And the last one, we call it V shape, and V script shape. We have, two set of pulleys on the system. Now we have a different arrangement and synthesis. We can have different arrangement to design different parallelogram length cable robotics. Look at this cable robotics versus this. We have two proposed design here. Let me just go through here. We are using three motors here, as you see, motor 1, 2, 3. The same thing here. Here we have four motors, 1, 2, 3, 4. And as you see here, by using some pulleys on the end effector or on the anchor point here, we can have a UVV structure. As you see here, we have a U structure on this drum, and for these two cables which are plotted in green, if you see, we have a script V cases. So this is one arrangement. We can have more than three motors. Of course, it is more expensive. We can have, and we have redundancy, and redundancy is always good in terms of kinematic and also in terms of different indices that we are considering. As you see here, this is a simple VV case. As you see, we have a V here, a green cable here, and the same thing with the blue, green, black, and red one with which are basically connected on the motors. Now, how effective is that? Is it any good or not? We also developed some systematic way to define the Jacobian or the kinetostatic modeling of that, and also to analyze how the stiffness is going and how the other measures of the kinematic measures and stiffness measures are going on here. These are quite simple. We go with the analysis on the cables, very simple loop closure that we are using. We can use the unit vector of the cables as the measure, like what has been used here. And in terms of kinetostatic modeling, we have some sort of the relation between the torque that we are using to the range that we are getting at the end effector. But now, since this torque is going through the different combination of cables, this U shall be found quite accurately. And from the U, we can find the structure matrix or the Jacobian matrix somehow to analyze the stiffness. Since I'm getting a bit low in time, I just go through a simple example as we have the previous example from the first one. Here you can see we have a UVV structure, a UVV structure, and then by just considering that the pulleys are ideal and the tension and the forces are equal to each other, we can get some row matrices that relates the torque from the winches to the end effector finally. If by doing this through this structure, we can simply find the structure matrix of the system as from the C matrix, we can find the U and then finding the structure matrix of the system. This is quite straightforward, and you can find it into the paper. And by doing that, now how we arrange the cable arrangement come into the structure of the C, and this will directly change the Jacobian matrix. Now we have the Jacobian matrix. We can now study different indices. The indices are quite well known. Of course, not only 4 exist here. We are representing only 4. We can have wrench closure workspace as the main important issue. Then we have some dexterity indices in terms of the singular values, or some stiffness indices in terms of the eigenvalues of the stiffness matrix. And also we have used the stiffness magnitude here. This is also proposed in the literature. And since we are up to a point that we would like to have more stiffness and faster response, we have also used the global measures here as indices. And finally, we compared different design now. Some parallelogram design with respect to some simple non-parallelogram design. Here we are considering just apple with apple. So 3 actuators here, 3 actuators here. These are traditional design without any parallelogram. And here we have the same UVV approach as you can see here. And then we go through different, just I give you some pictures. That picture gives more than 1,000 words. Here you can see the this is the parallelogram case, and this is the simple case. Our workspace has been increased, not only the workspace, but the dexterity of this, the dexterity index of this design is getting much better than the traditional design. The dexterity is not that great, but in terms of elastic stiffness, you can see that we have much better stiffness here, especially in this area. And then in the stiffness magnitude, we are quite better. You know, as you see here, we are up to 7, and here is up to 3. So the design here becomes much more stiffer as we expected from the design. Just going to another case, of course, there are 100 different types that can be measured. We go through the redundant case. If we have 4 motors, what will be happening if we have redundant case? We can see that in the redundant case, we have a full workspace for the system, both cases, but again, the parallelogram gives us a lot better dexterity in terms of compared to the conventional case. And in terms of elastic, you can see it is maybe 10 times better. It is quite significantly better. And in terms of magnitude indexes, you can see again, we are much, much better here in this case. So this is a proof of concept somehow. It seems that if we are using the case, we can also just make all the comparison together. Different measures are be considered for different design. Of course, the redundant cases that are in these 2 colors will give us the most work wrench feasible or wrench closure workspace, of course, but there are more expensive and a bit difficult to make it, commercialize it. But rather than that, we can see that in terms of other indices, other optimization indices, the structure of the UVV design is quite good and comparable even to the redundant cases. Especially in GSM, we can see that this is getting much better. Now, To make it finalized, we did a experimental setup on a prototype, the Camel Milk 2, of course, with a simple structure to make the proof of concept in here. As you can see here, this is the speed is not increased. This is the real speed of the robot. The accuracy and speed comes much more better than the previous one. I will finalize my talk about, again, like what Darwin says, we have an application in mind and we need to develop theories and fundamental theories for that, as you can see in here. I should mention many names here. Since the time is low, I will just leave the names here and give just some picture of the people who are working. Hopefully, we have quite a large group of researchers working with us. This picture is a bit older. Some graduates are here, and this has been taken, I guess, yesterday, and I am missing in this picture. Thank you very much for your time and attention. I am open to your question. Thanks, Philip.
Okay, Hamid. Any questions? Oh, Marco, do you have a question? I can't hear you though.
Oh, can you hear me?
Yeah, now I hear you.
Okay, I wish to ask to Hamid, well, first, congratulations for your work. Which kind of control do you implement on your cable? Just pure force control or something different in order to get the accuracy that you were showing us also in your picture?
Unfortunately, I didn't have time to talk about the control. We are using two types of controls, basically, two different types of controls. One type of the controls are usually, we have an internal force feedback and an external position control. And usually we are using the loop closure and the Jacobian matrix to make sure that everything that the cables are all in tension. But also from last year, we are starting some non-model based control, like the iterative control that Darwin told us. We have used Bell-Bic. This is one case of control that is just doesn't need any model. Of course, it needs a bit knowledge about the Jacobian and also time delay control. This is another way that is data-driven control. We have worked a lot on the control in our past research, in nonlinear robust control, but now we are just changing our avenue to see simpler and more learning-based control can be used on the system.
Okay, Tobias, you had a question?
Yeah, thanks, Hamid, for the very inspiring talk. I have a question regarding also the painting application, because I think there's lots of potential if drawings or paintings are large, right? So would you have an idea up to which scale you would be able to generate enough pressure to really do a painting with that approach?
Yes, actually, maybe the first incentive for us, if you come to Tehran, and I hope that I can sometime invite you all to come and visit Tehran sometime. We have very tall buildings that are painted with different pictures. And we have more than 2,000 very large buildings that should be painted. And of course, painting in Tehran needs to be repainted again and again after a while. Our idea is like what Darwin showed regarding the window washing case for very large painting, like let's say maybe 30 meters tall, 10 meters wide. But we have not really implemented it at that scale yet. But we are hoping we are doing that. There is another also application, just inspiring application. You have some billboards everywhere. You will see billboards on the freeways, some on top of it and some on the side. And it is very interesting if a robot is writing or painting on the billboard, not just something fixed is on top of that. This is also another idea that we can see. The workspace there would be 2-3 meters to 6-8 meters long.
Thank you.
You're welcome.
Okay, maybe a question from Yogesh Singh.
Yeah, hello, sir, I'm audible.
Yes, of course.
Yeah, good evening, sir. Sir, I have a question that you talked about Jacobian matrix, and there is something called singularity in Jacobian matrix. So, like, what is the problem that this singularity can create in this type of robot? And how did you ensure that, like, we did not enter into this singular configuration?
A very good question. If you are familiar with parallel or with cable robotics, you know, not only the singularity, but there is one more degree of redundancy needed more than singularity to avoid the cables to become into, to be always in the tension. If the robot becomes singular, you know, it is far away. One step before that is the robot becomes, you know, that we cannot, you know, get the tension on the cables. That's why we call it the wrench, you know, feasible workspace or this kind of situation. And there are a lot of kinematic approaches to make sure that within which workspace you can do that without singularity. So all this, as you can see, all the workspace that I show you are all singular free. Not only singular free, there are fully applicable by tensile forces.
Thank you.
Thank you. Yeah, so I think wrench feasibility supersedes singularities. If you are wrench feasible, then you're guaranteed to have no singularity. Okay. Thank you, Hamid, for this nice talk. I think we can move on to our next speaker. Stéphane, are you here?
Yeah, Philippe. Yeah.
Okay. Hello, Stéphane. Can you share your screen?
Can you see my screen?
Yes. Whenever you're ready.
Okay, so hello everybody. So thank you very much, Philippe and Hamid, for the very kind invitation to this workshop. I'm very happy to also to meet some other colleagues here today. Unfortunately, not in person, but at least this is better than nothing online. This is very nice. So hello everybody. So first, I wanted to emphasize that in the program, my presentation was entitled the CDPR and industrial applications. So it was the first at the time. I didn't know exactly what I would have presented today. So I will talk about some industrial applications that we are focusing in Nantes with the CDPR, but mainly I will focus later on some work we did, mainly in the scope of the doctorate thesis of Tahir Rashid on the mobile CDPR. And so it also deals with industrial applications. So, okay, no need to recall what the CDPR is, but here So in the main motivation of this work was to develop a new kind of CDPR in order to, or new kind of reconfigurable CDPR, mainly in order to avoid cable collisions and cable collisions and collisions in between the cables and the environment, while keeping good performance indices such as stiffness, range capability, and so on. So here, okay, so those are some pictures of existing CDPRs that most of you know quite well. So let me give you a focus on some CDPR for those who are not aware of our work in Nantes. Some CDPR we developed both at IRT Jules Verne, which is a technological research institute located in Nantes, and LS2N is mainly the work where I work, so Laboratoire des Sciences du Numérique de Nantes. And so I'm working in those two institutes, mainly today on the modeling, design and control of CDPR. So here are some pictures of some prototypes that we have realized in the last few years. I have a video. I can show this. Hopefully it will be okay. So here this video shows some okay, just a summary of some prototypes we developed with a focus on specific industrial applications. So I will come back to those mobile CDPR later on. So here we have okay. So here we have an animation. I mean, video of Facades, which is a mobile CDPR composed of two mobile bays, one passive one and one active one, dedicated to logistics. So this one is composed of 4 active mobile bases, focusing on pick and place operations in large spaces and workshops. So we have been working a lot also on the control, mainly for the model-based control of CDPR with where we can focus on the cable tension management by using a robust controller. Some work also done in the visual servoing of CDPR with a focus on the state stability of the controller. So here we mainly focused on the visual servoing with embedded camera, and some current work on the collaborative CDPR with focus on the determination of standards and recommendations for the development of such robots. Another type of reconfigurable CDPR is so here we simply replace the mobile bases by some aerial drones. And, so it's not a bit fast. Maybe I can come back to this one. So here in this work, so all is somehow so those prototypes are all different from one another, but they are very close in terms of modeling and the performance analysis. For instance, in this work, we focus on the range capability analysis of such a simple ACTS composed of 3 aerial drones and 1 point mass in the effector. So unfortunately, in this video, we can hardly see the cable, but indeed, there are some cables connecting the drone, the 3 drones, and the point mass and effector. And some also in the team, in Roma's team, we have a strong activities and also on the construction robotics. And we have some ongoing work on the additive manufacturing using CDPR as a mobility solution. I will come back to this project later on, this new project. So here, our main, one of the specificity of our work on CDPR is deals with reconfiguration of such a robot. So again, we're not the first one focusing on the reconfiguration of cable-driven power robots. So here are some on the left some pictures of some existing reconfigurable and mobile CDPR. Okay, and at the upper left, CDPR, mobile CDPR composed of some mobile basis, and here at the lower left, bottom left, sorry, mobile CDPR with the pulleys moving along some guides, some rails. Okay, so I talk about this other kind of reconfigurable CDPR, the IL cable towed system. This one developed at Lausanne, and the well-known flight crane developed at Toulouse. So this is a picture of a Caroca prototypes, and this is the first reconfigurable CDPR that we developed. And here, with this CDPR, the reconfiguration is somehow discrete, meaning that we can move the position of the pulleys of the cable exit points in a discrete manner along the blue bars of this prototype, and the blue bars themselves can be also moved in their plane in a discrete manner. So here, the main motivation of this CDPR was to somehow to find some solutions in order to get rid of the cable-cable collisions and the collision between the cables themselves and the environment. Okay, so here the targeted application was to sandblast and paint very large structures, both inside and outside. So for this specific application, we needed the CDPR to reconfigure. So now to come back to the main focus of this presentation, I will mainly show you some results, some contributions we came up with on the performance analysis and then also on the trajectory planning of mobile CDPR. So here, this is the concept of this mobile CDPR. So here, those are the two prototypes. I've already shown you some videos of those two prototypes we mainly focused on in the scope of this work. So the first one, which takes the cablar configurations defined proposed by Tobias Bogman, but on top of two mobile bases, one active and one passive one. And the targeted applications here is clearly logistics. And on the right, this is a mobile CDPR composed of four active mobile bases and a simple point mass end effector. So here in this work, we mainly focused on the static equilibrium of such a system. So it makes sense that the mobile CDPR is in a static equilibrium as long as its moving platform is in a static equilibrium and its mobile bases are both also in static equilibrium with respect to their tipping conditions and sliding conditions. So this is okay. So just to sum up, the main contributions of this work was to consider the tipping conditions and sliding conditions of the mobile basis in the range capability analysis of this type of robot, and also in the tension distribution algorithm of this type of robot, tension distribution and management. So if we do not consider the mobile basis, for sure, in order to analyze the static equilibrium of the moving platform, we simply need to analyze the range matrix and to consider to analyze all the conditions for which the moving platform can be in a static equilibrium while respecting the cable tension limits. So here in the scope of this work, we assumed that the cables, for a matter of simplicity, that the cables are straight and massless. And here, so now if we consider the tipping conditions, okay, so without considering the tipping conditions, for sure here the mobile base tip as soon as the ZMP of the moving platform is out of the area bounded by the contact point between the wheels and the ground. So here for this, for example, for this GIS mobile base, so this GIS mobile base will remain in a static equilibrium as long as this moment, this quantity here, is lower or equal than 0, and this quantity is directly a function of the cable tension and the cable arrangement onto the mobile base. And so sure, it's also a function of the rate and the first moment of inertia of the mobile base. So we did also consider the sliding conditions. So here we cheated a bit in order to simplify the problem. Here we assume that we linearized the friction cone in order to end up with a linear inequality characterizing the sliding or the non-sliding conditions of the mobile basis. So by doing this, we are a bit pessimistic, but we simplify the static equilibrium analysis of the MCDPR. So then, in order to correctly manage the cable tension, okay, so here we used, so we also considered those tipping conditions and sliding conditions of the mobile basis in order to determine the modified feasible polygon of the MCDPR for a given moving platform pose. So it's well known that for classical CDPR, this feasible polygon has such a shape, and in the lambda space or in the kernel of the range matrix. So here, what we did here, we projected the tipping conditions of the mobile basis and their sliding conditions into the lambda space in order to determine the modified feasible polygon for such a manipulator. So here I have some just a small animation showing clearly the contribution of this work. So if we do not pay attention to the tipping and sliding conditions of the mobile basis, so here the mobile base may tip along when the moving platform follow the prescribed path. However, by considering the tipping conditions or sliding conditions into for the determination of this feasible polygon, we make sure that the mobile basis won't tip nor slide when the n effector follows a prescribed path. Okay, so now in terms, we also focused on the range analysis and many range feasible workspace analysis of MCDPR. So here we did consider those sliding and tipping conditions of the mobile basis to determine first the modified tension space, cable tension space, and then by using the range matrix we can determine the modified available range set for a given position, for a given pose of the moving platform. So here, Darwin presented different approaches to analyze the workspace of CDPR. Here we first focus of straightforward. We first use the straightforward approach, which is a convex hull approach, in order to determine the available range set of MCDPR. Okay, so this is quite very easy to apply, but can be a bit time consuming and not very elegant. And we also used here the hyperplane shifting method in order to determine the hyperplanes associated with the cable tension limits, tipping conditions, and sliding conditions of the mobile basis for the determination of the available range set of the manipulator. Okay, maybe I can skip a bit some math. So actually, this approach is clearly well defined, presented in this paper of Bouchard and al. And but here the main contributions here deals with the consideration again of tipping and sliding conditions of the mobile basis in order to determine the upper planes associated with those conditions. So for sure, by considering, unfortunately, by considering those tipping and sliding conditions, the workspace of the manipulator is shrunk. But this is important to analyze to consider those conditions into the determination of the workspace of the manipulator. So here I will show you. Maybe I will move here. Okay, so here, so this is some work we did some time ago. On the so here we have so here the green. So for example, in this plot, okay, it makes sense. The green area is correspond to the workspace of the manipulator while considering only the cable tension limits. And in the blue area, we know that one mobile base will tip, and in the red area, we know that one mobile base will slide according to the range analysis. And here we can clearly see that for this very simple mobile Cdpr, the simulation results and match with experimental results. And here this is the workspace of okay. So here in this animation, the green area represents the modified and real workspace of this MCDPR. Okay, so we can notice that unfortunately for such a robot, this workspace, the green workspace, is much smaller than the gray one. The gray one corresponding to somehow to the Cabler workspace with the Cabler configuration workspace. Okay, I can skip this part. I will move forward with the path planning. So one challenge with such robots is to deal with the kinematic redundancy of the manipulator. So mainly when we have several mobile bases. So here we first consider the case in which we have only two mobile bases, one passive and one active, and the case in which the robot moves in a plane, for which we have only 4 cables. So here we first formulated in a very simple way the kinematic redundancy planning problem of such a manipulator. For example, we formulated the problem as follows. This problem aims at first and minimize the total time required to follow the prescribed path, and also to maximize the range capability of the moving platform along this path, and while satisfying a set of constraints. So here, for instance, by solving this problem, okay, we obtain those non-dominated solutions for the kinematic redundancy planning of this planar MCDPR. Okay, the solutions are also named the Pareto optimal solutions. But then, okay, so we used somehow. We also use the direct transcription optimization technique in order to determine the path of planar and the spatial mobile CDPR. So the program is defined as follows. So first we define some waypoints, okay, to be reached by the end effector into the workshop, and we assume that we know the location of the obstacles in this area. So here the path is divided into a set of discrete points, some discrete points associated with the end effector and some associated with the location of the mobile basis. And here the objective of the problem here is to find the state, okay, that maximizes the range capability of the system while minimizing the distance traveled by the mobile basis. And here we consider the obstacle avoidance and also the cable length limits. And here's what is important to notice: by solving this optimization problem, we should make sure that those equality constraints are satisfied. Those equality constraints, considering the velocity of this, I mean, the first derivative of this state vector. So by using this technique, okay, we can notice that it is a much more efficient than by using the first our first approach. So by solving this optimization problem, we find the optimal location for the mobile basis and the end effector for the end effector to go through all the waypoints in this cluttered environment. We also here generated a simulator of this system and the VREP, the Copelia sim, in order to validate those results in the simulation. And I think that I have also an experimental validation of this work. Okay, I think that I have. I don't know how much time I have, Philippe, to conclude. So here to sum up, okay. So those. So
I think you have 2 minutes. Sorry.
Okay, perfect, Philippe. So just to sum up, to conclude. So here in Nantes, the last few years we have been working, quite a lot on the design, modeling, and control of reconfigurable cable-driven power robots. And here today I gave you a focus on some work we did on the modeling and the path planning of mobile CDPR. For sure, there is still a lot to be done. So in this work, for instance, we assume that we didn't consider the properties of the cables. We assume that the cables are massless and non-elastic, okay, which is not the case for sure in practice for very large mobile CDPR. And for the localization of the MCDPR, we simply used some embedded camera to define to measure the location of the mobile basis with respect to one to another. So we could also investigate other techniques for the localization of the mobile basis. And we should also consider this is some ongoing work, also with some collaborators and the dynamic. We should also consider the dynamic behavior of those mobile CDPR for sure, mainly for high-speed motions with such a system. And just for your information, so this is also an invitation for you to join this project in the next few years. So here in France, we have just got this very large, big project named T-Rex accepted. And this T-Rex, this is a national project, and it will start in December and will last until 2028. And in the scope of this project, we will build 6 robotics platform in France and on different fields. And one of them will be dedicated to, is named XXL Robotics and will be located in Nantes. And this platform will be composed of at least of a very large CDPR with an embedded serial arm. And this platform will be open to collaborations, national collaborations for sure, and also international collaborations. Hopefully, we will have the opportunity to work together and for you to also to work on this platform if you are interested in it. And at least in France, so LIRM, P-Prime Institute, INRIA, and LF2N are directly involved in the development of this platform. And the targeted applications, so there are also some industrial partners involved in this project, such as Airbus, so different, and also so the targeted applications are mainly manufacturing and construction robotics, and also, yeah. Okay, so that's the end of my talk. So thank you very much for the attention, and feel free to ask me if you have any question. And again, thank you, Philippe and Hamid, for the very kind invitation to attend this workshop and to take part in this workshop.
Thank you, and thanks to you, Stéphane, for participating and for this nice talk. Any questions for Stéphane? I might have one question. In the fast kit system with the mobile robots and the mobile robots moving the anchor points of the cable robot, could you use the mobile robots to cancel the out of plane oscillations of the cable robot if they occur, or
I mean, for this fast kit?
Yes.
Yeah, I think this is a good question. Actually, with this system, for sure, we face with some oscillation of the platform, of the moving platform along the normal to the plane of motion, but we didn't play with the mobile base to attenuate those oscillations. Actually, with those mobile base, at least if we have some some omnidirectional wheels, maybe I think this would be a very good idea to use a mobile base in order to attenuate those oscillations. But at least I think we should first play, with the actuators of the CDPR itself in order to attenuate as much as possible those oscillations of the mobile of the moving platform.
Mm-hmm.
But I've never thought of using the mobile basis to attenuate those oscillations. But I think this is a very good idea, but not with those, not with this type of wheels.
Yeah, okay. Yeah. Okay, because I know Amir Kajepour, I think, and Rushton, I can't remember his first name. Okay. I think they published a paper where they used, I think, masses, rotating masses, and the gyroscopic effect on the moving platform to cancel those out of plane vibrations. Okay. And that's what made me think, well, if you have a mobile base, then maybe you could cancel that. But
actually, we didn't think of it, but I think this is a good idea. But I think that okay, so it's worth investigating.
Yeah. It's just an idea like that. Okay, Tobias has his hand raised. Go ahead, Tobias.
Yeah, thank you. Stéphane, a short question regarding energy consumption, because you have a mobile application, yeah, so you always have to carry your energy with you. And now you have those drives which are basically always counteracting to maintain inner tension. So I assume that, well, there is some energy that is needed at any time, point in time during operation. Did you make the experience that this could be a critical thing, or do you have the impression that the power or the energy that current battery concepts can maintain is sufficient for things like this, say for an 8-hour shift or something?
I think this is a very good question regarding, I mean, for sure, what we have in mind with those CDPR is with those mobile bases. I mean, the mobile bases, okay. Here, for example, for sure in this video, we may think that the mobile bases are always moving. And so here the mobile bases are used in order to somehow to reconfigure the CDPR. So they're not made to move all time long, but mainly to reconfigure the robot. So what we have in mind is to mainly use such reconfigurable robot, and to use the mobile base to first reconfigure the robot, and then to use the CDPR, okay, as a classical with CDPR as soon as the mobile base are fixed. So for sure, we need some energy. The mobile base should carry and need some energy to carry the actuators. I mean the actuators of the CDPR. Okay, so this is for sure in terms of so we need that energy. But as soon as the MCDPR is reconfigured, so it can work as a classical CDPR, but still we should embed the energy onto the mobile base.
I think this thing gets worse if you have a fully tangent configuration, right? So if you have really like say 8 cables or something that are creating inner tension, that could be a different situation, right? If you have to carry all the energy on board for all those 8 drives, that might also counteract.
Yeah, that is true. That is true. Yeah. So what we have in mind, I mean, the main motivation behind this work was to use very large crane, sourced, and those cranes, so a very large forklift, okay, and what we plan to do, our idea was to use the energy of those cranes, of those forklift, to actuate the winch.
Okay. Yeah. Okay. Thank you.
But that is true. We need in that case we need to embed the energy.
Okay. Thank you, Stefan.
Yeah. You're welcome, Tobias.
So in the interest of time, let's move on to Tobias. Tobias, don't turn off your microphone. Thank you, Stefan, for the nice presentation. And
thank you.
Tobias is going to talk to us about the transfer of cable robots into applications for construction automation.
Yes.
So go ahead.
How do you see the future of the CDPRs? We have seen a lot of interesting applications in the first session, and we will see some further theoretical development in the second session. But we would like to just be freely, talking about the current status and the future point in cable robotics.
Oh, Tobias?
Yeah, I think Stefan raised a quite important aspect, right? So as I said, our experience is cable robots are meanwhile able to just do that job. But the thing is that all the things around have to work as well and have to contribute. And many processes that we saw in the last presentations are typically not done by robots. That means all auxiliary processes are not prepared for automated operation. And I think one of the challenges that we will have in the future is to find people that are from those fields who are willing to think about automation, who are willing to introduce cable robots, and who are willing to change their processes to allow application of cable robots. And our main job will be to convince them, I think. Yeah, so we have to be better in marketing in the end. That's my impression.
I mean, to follow on Tobias' point, don't we need some inherently safe cable robots? Could we think of ways to make cable robots more acceptable? Say, show that you cannot exceed a certain tension in the cables or things like that. Of course, you have to still be able to move the payload, but could we think of some innovation there to make them more ready for collaboration?
Sure. Marco, can we have your focus here too?
Sure. Actually, I was thinking that there is. Oh, first, can you hear me? I know that my microphone.
Yes, sure.
Application fields where there is the most ancient cable machines in human history, which is a crane. And not many people speak about security of the system, which are basically everywhere. The payload oscillates, there are people around, having other cables trying to hold the cables. And this system still instructions, lifting, logistics, and they have been working for thousands for centuries.
Marco, we can hardly hear you, Marco. I think that your mic maybe is a bit far. Yeah. Or maybe this is my connection. Yeah.
Can you, did you hear me?
We have on and off, you know, we hear you, but it is on and off.
This will be a problem for my presentation. I really don't know what to do. So I will try to change computer later. So I was saying that since cranes are everywhere and they have security and safety issues as well, anytime we add one cable, basically we are all increasing safety. And because if the cable breaks in the crane, that's it. I mean, if we have two, at least we have one. I mean, I sometimes of room for the application of our cable systems in the domains where cranes are already used, which are not the domains that were probably focused on by your excellent talks today. But still, I mean, those domains should be attackable, and probably they should be the first to attack. So instead, rarely go in that direction. And speaking to those people, basically, they start worrying about the fact that we have many cables. These cables can be around, there can be safety issues. I rarely hear those same people speaking about the safety of the systems that they are using today. So probably we should try to convince them that our technology is not really that different compared to what they are already using. Simply works better and it is safer because it is more redundant.
Perfect. Thanks, Marco. Darwin, do you have anything to add?
Yeah, yeah. So I guess regarding acceptability and like safety, I think it really depends on what we're comparing it to, right? So it depends on where we're using the robots. So for example, as Marco says, we're using it in the construction industry. In fact, they're used to dangerous machinery, right? So as long as we're able to have either existing protocols, like for example, some of the projects we use for now, we don't try to invent a new protocol for the government. We just say use the same as a gondola, right? We are lighter than a gondola, but we could use the gondola protocol. And then for some other cases, in fact, if we're using a robot to replace, let's say, something that would be done using a tow truck or a crane, the robot would naturally already be either less heavy duty or safer anyway. So I think, in that context, if we're targeting certain applications like construction, which has appeared quite a few times, then I think, safety may not be as big of a concern given that they're already used to protocols to prevent them, right? But I guess in some other cases, it may be, need more convincing, probably.
Thank you, Darwin. Stefan, I would like to ask you your opinion about just not the safety, maybe the fault tolerant cases, or maybe also there are some open questions regarding cable-driven robots. What do you think about it?
Oh, okay. Thank you, Amit. So for sure, there's still open questions. But just to come back to the safety issues. And I think that based on my small experience on the CDPR, I think that what we are missing, at least, I mean, I'm talking about in France, okay, because we have been working with many, industrial partners, okay, interested in the concept, you know. So we are quite lucky in Nantes because we have some companies such as Airbus, Chantier de l'Atlantique, Naval Group. So many companies were working in very large workspace, not directly related to construction industry, but manufacturing industry. And they are still very interested in CDPR. So I don't know, maybe we're not convincing enough for them to bring a real CDPR on site. But I think that what we are really missing, maybe this is not the case on your side, guys, but this is really a systems integrator. And we have been, recently I've been liaising with a company building some kind of SkyCam. Okay, this is a company in France building, not SkyCam, but this is under another name. And they build everything from scratch. You know, they don't even know what I was very surprised, because those people don't know us. You know, they don't know us. They don't know the CDPR community. But they built everything from scratch without paying that much attention to the math, to the mathematical model, and so on. But mainly they defined their own standards. They defined their own standards in order to commercialize their system worldwide. So I was quite I was quite impressed by their work. For sure, they cannot communicate. This is very confidential. That's how they make money. But at least what we really need to switch from our academic contributions to somehow the real world is really a systems integrator. But this system integrator, they really need those standards. So there is in between. So first, we should already. Recently, we have been working on a project named Cover. Maybe Tobias knows this. This is a very big project, a European project dealing with collaborative robots. Not only CDPR, but we got a small funding to work on the normative recommendations for CDPR and for CDPR collaborating with human. But still, this is a small project, but I think that all of us, we should really work all together to define, and this for sure, this is not sexy, you know, this is not as interesting as tracing a very nice workspaces, such as what Tobias showed, but it is very important for, in my opinion, to convince and to help the system integrator take and sell the technology. And this is my main feeling. So it has nothing to do with, again, with academic research, but our work can definitely help building and writing those standards. And this is what I feel. So this is a bit frustrating because at least in Nantes, again, I have had the chance to communicate with many industrial partners. Okay, so we built some nice projects. Okay, I'm quite proud of this, but no real industrial solution yet. I know that it takes time, but this is really, to me, this is one of the key points that we really miss today. And regarding the open problems, for sure, there are still many open problems, but some of you are already working on it. In terms of Philippe Cardou talked about oscillations. So at least I think there is a room here for contributions. If we want to improve the accuracy of our system, definitely we should keep on working on the elastodynamic modeling and oscillation attenuation of our CDPR, while considering the complex CDPR model, while considering the cable sagging, cable elasticity. All this usually is neglected. And something else, many companies also often they ask real, simulators, no? And so as far as we are concerned, we have been working with some our own simulators made under CopyLSIM, but they are not very realistic. So I don't know, guys, whether you developed on your side, realistic simulators. but I think that this is also missing, in my opinion. And all our work in terms of modeling and also control should contribute in the development of more realistic and low time-consuming simulator of CDPR. Instead of okay, so this may be that's part. Okay, this is what I wanted to say, but amongst many other things.
Thank you.
So I don't know what you think of this.
Yeah, perfect. I would like to hear more from the audience as well, but Dominic is with us as well. Dominic, can you also give any comments on that?
Just enter the discussion, so it's going to be hard for me to comment, but yeah, maybe I have a question to Stefan. So you mentioned about there is something missing, which is the simulator of cable robots. That's what you're saying. Just
yeah,
now?
I think that okay. Bonjour, Dominic. So I think that this is one of the okay. So very often so at least in Nantes we build several prototypes. Actually, in order to test and implement different control schemes, and also for mainly also for demonstrations for our industrial partners. But we try to develop our own simulator. Okay, for instance, under Copelia Sim, but they are not very realistic. They are good to make some demonstration, but not really to validate some and to test some different control schemes. And for instance, we cannot really we cannot really model the cable break and the behavior of the cable with the simulator we created. Okay, maybe that's what I was saying. And
are there some existing software, simulation software, in MATLAB or Python or whatever?
Yeah, I mean, we can make we can somehow animate and not really simulate, but animate CDPR with MATLAB or Python. But this is not really. This is very difficult to model the behavior of the cable. Okay, mainly cable considering their mass and sagging. Okay, as long as the cable is very thin, light, massless, that's fine. But for large size CDPR, we cannot make this assumption anymore, in my opinion. I don't know. Maybe I'm sure that Tobias, Darwin, Marco will comment on this. Maybe for some people, such as I don't want to talk about instead of Jean-Pierre, but Jean-Pierre considers that for sure it doesn't make any sense. It doesn't make any sense to build a simulator. Okay, so no way we will be able to develop a simulator. But very often it could be at least for us it would have been very convenient to have to have a real and a realistic simulator of CDPR. I don't know what guys you think of this.
Well, what we always do is before. I mean, this was also the case for the construction demonstrator. What happens if you want to build a demonstrator? You need a hall. Yeah, you need some place to erect it, and then someone tells you, okay, this is the building to be created. And what we did is indeed we used a more or less realistic model. I mean, it was sufficiently realistic to check, is the workspace large enough? And we used the same model to do the dimensioning, say, for actuators, for sensors, for the winches, torque, power, energy. Yeah, all these things were checked in advance. So I think that say cable robot engineering for applications in the future will indeed be dependent on models that are sufficiently realistic enough. Yeah, I think this is an extremely reasonable tool for cable robot development, because we will never be in the situation that some educated engineer says, that's the application, I know how this cable robot should look like. This is the cable arrangement. This is the frame size. These are the force limits. That will work. Yeah, I don't think we will be in that situation at any point in time. It would always need models to do the dimensioning, I think.
Perfect. We are running out of time. Eduardo, Muhammad, and Ryan didn't talk. And also, if there is anything you guys would like to add, please, we have 2-3 minutes left.
I can add something. I'll say, you know, so I'm in an aerospace engineering department. That's kind of my background. So a little bit outside of robotics, but I am very interested in CDPRs, of course. I think there's some insight we can gain from aerospace engineering. I would say both in terms of applications and theory that we can use. So, you know, I see that, you know, there was some really great discussions today on kind of some open problems. There's going to be a lot of talk about control in the second half. One thing I would mention, because I don't think it's going to be emphasized, is the estimation side, and it's the sensing side. And I think there is a lot that can be taken from aerospace engineering. There's a lot of work that's been done with GPS algorithms for that, inertial navigation, and how you kind of fuse that all together in ways that get you very good, you know, accurate solutions. So that's something that I've become very interested in lately with CDPRs, and something I think would be worth looking into in this community. And in terms of applications, I think space robots would be a very interesting thing for the community to kind of get into a little bit more. I think it's actually kind of an ideal situation where, you know, we need lightweight structures. We need things that can operate over very, very large workspaces. Of course, there are some interesting challenges there too. They're not going to be necessarily the standard CDPR structures that we think of, you know, on Earth. But, you know, people like NASA, you know, are already considering this. They have these tensegrity-based space manipulators that are going to be using cables for actuation. There's already talk of building a radio telescope on the dark side of the moon using, you know, kind of the same technology that the Arecibo telescope used, right? So anyway, so I'm just bringing my perspective as an aerospace engineer. I think there's some interesting applications there. They'll require some interesting designs. And I think, especially on the estimation side, I think there's some really cool insight we can get from aerospace.
Perfect. Thank you very much, everybody, for their contribution in this discussion. I'm very sorry that we started a bit late, and to close at the right time, we have to start the next session that Ryan is the chair. So I would like to ask Ryan to please open your microphone again, don't close it, and start the second session as you wish. Thank you.
Sure. All right. So for those who don't know me, I'm Ryan Caverly, an assistant professor at the University of Minnesota. I'm in the Department of Aerospace Engineering and Mechanics. So given why I was talking a lot about aerospace. So it is my pleasure to be chairing the second half of this workshop, which is going to be on parallel and cable robot frontiers. So we do have 4 presentations in this session. And so it is my pleasure to introduce the first presentation, which is going to be given by Marco Caricado and Eduardo Ida on theoretical and practical challenges of underactuated cable-driven parallel robots. So I'm not sure which one of you plans on sharing your screen, but I suggest you go ahead.
Okay, well, first I would like to ask you if you can hear me properly this time. I'm trying to switch computers.
This seems better than before.
Thank you.
It is much better.
Better than before. Much better. Thank you.
Better.
So, can you see my screen?
Not yet.
Not yet. That's bizarre. Let's try another option. What about now?
That looks good on my end.
Okay, thank you very much. So thank you very much for letting me and Eduardo here with you today to discuss about our underactivated cable-driven parallel robots, which is a kind of weird CDPR that normally receives little attention, at least in our community. We'll speak about some theoretical and practical challenges that these very peculiar systems offer. My speech will be mainly dedicated to some classification of the systems and a little bit of modeling, geometrical static modeling. Then I will leave the stage to Eduardo that will speak to you about more detailed challenges, scientific type challenges concerning workspace characterization, dynamics, parameter identification, and trajectory planning. Now, probably the most common classification of CDPRs that you know, that you are aware of, is the one that comes from an old work by Ming and Higuchi that in back from the 90s. That was followed by many in our community later on. According to this classification, mainly CDPRs are classified according to the number of cables, N, the number of degrees of freedom of the end effector, and F in general, but we can set this number just equal to 6, just to be, just to have a simpler number in mind. And according to this classification, when N is not greater than NF, the robot is considered under constraint. Basically, according to this definition, the two systems that you see in this slide are, I'll just use, sorry, okay, the pointer. According to this classification, these two systems are considered under constraint because in the first case, we have 4 cables, which is smaller than the degrees of freedom of the payload. And in the second figure, we have 6, which is exactly equal to 6. And then the robot is considered completely constrained if we have one more cable, namely if we have one cable more than the number of degrees of freedom. And based on this classification, the two figures that I'm showing you are still considered the same. The idea behind this classification is that since cables can work only if they are towed, we need an extra cable in order to let them be towed. Basically, we want to use the principle of pulling the cable against each other, so that if we have an extra cable, we can use it in order to increase tensions in the other and prevent the old cables to become slack. But clearly, this only works if the cables are located all around the payload, like in the second figure. This is not the case of the first one, and this is the first deficiency of this classification. Then robots are considered redundantly constrained if we have even more cables. So we don't only use the single cable that I mentioned before in order to pull the other ones, but we have at least 2. But even in this case, we must consider the fact that if we want to use the strategy, we at least need to set all cables around the moving platform. Most robots that are studied in our community are of this completely or redundantly constrained systems according to this classification. Basically, because in order to control the robot, most people would like to have, to be able to use cables in order to ensure tension in the other cables as well. And that's the reason also because so that most of the systems studied have cables all around the moving platform, like in the video, which is drawn from Tobias' team, which is, however, pose some problem because, of course, it poses some limits to accessibility in the area around the end effector. The classification that we've been using, however, is fairly different because it's not based on the principle that I mentioned before, but it's based on classical mechanics, where there are very simple but strict rules in order to classify systems as under constraint, completely constrained, or over constrained. And these rules are well established in rigid body mechanics. We have to consider not only the number of cables, but more precisely the instantaneous number of towed cables, which I will call N-tow. And we will compare N-tow with the number of freedoms of the platform. If N-tow is strictly smaller than the number of freedom, we will have an under-constrained system. Otherwise, we will have a completely constrained system if those two numbers are equal. Or if N-tow is bigger than the number of freedoms, we will have an over-constrained or redundantly constrained system. This is the established classification in rigid body mechanics, and the reason is what I will discuss in the next slides. Why do we have to consider the instantaneous number of towed cables? Because basically a cable is active only if it is towed. If it is slack, like in the figure at the right-hand side, basically, I mean, I'm pointing at this cable here and this cable here. It's like the cables are non-existing. So they do not set any kinematic constraint and they do not even set a static range constraint on the platform. So basically in this, even if the number of available cables in both cases is different, basically these two systems behave in the same way. And any cable can become instantaneously slack, even if their number is 4, is 6, is 7, and 8. And actually, the problem of slackness is I'm sure that is very, I mean, you are very aware of this problem, whichever is your background. Now, as I mentioned, an active cable is a cable that is towed, and a towed cable establishes one kinematic equation and one constraint range on the platform. So basically, the constraint that is provided by the cable works in these two directions, both in kinematics and in mechanical equilibrium. How many kinematic loop closure equation may we write? Clearly, one for each active cable, so N-tow. How many mechanical equilibrium equation can we write generally in space 6? So the overall number of equations that we have will always be, at least in rigid body mechanics, which is what I'm focused now today, will be N-tow plus the number of freedoms. Let's say N-tow plus 6. How many input variables do we have? Clearly, one for each active cables, overall number N-tow. And how many output variables do we have? Well, tensions in the cables, which will be always unknowns, and the post variables, 6. So basically, we realize that we have the number of output variables is always equal to the number of equations that are available. So if we consider kinematics and statics, we are always, and the input variables are assigned, we are always able to find a solution for this problem, and the number of solutions will be a discrete number. However, if we consider them together, what if we consider them only, independently? If we have to distinguish if the robot is under constraint according to our definition or not. If the robot is under constraint under our definition, the number of active cable is strictly smaller than the number of freedoms. And well, in this case, the number of kinematic equation is smaller than the number of end effector post variables that we want to compute. This means that kinematic is not sufficient to determine the end effector pose because the end effector, once the kinematic constraints are imposed, is still have some freedoms that are not saturated. However, if we go back and consider kinematic and statics together, the problem is perfectly solvable. So the peculiarity of under constraint system is this, that kinematic is not sufficient to determine the pose of the end effector, but if we consider mechanical equilibrium as well, we can determine it. So kinematics and statics are coupled and they must be solved simultaneously. If instead the number of towed cables is instantaneously equal to the number of freedoms, the situation is completely different. Because in this way, we have as many kinematic equations than as the number of end effector post variables that we want to compute. So in this case, kinematics is sufficient to determine the EE pose. And we have also as many equilibrium equations that cable tension that we want to find. So even in this case, statics is sufficient to determine cable tensions, and the solution will be unique because the problem is linear. So kinematics and statics are decoupled and they can be solved independently. And this is true even for the system here, which is suspended by only 6 cables that are towed in this configuration, this instant. So we see that considering together the previous case, like in the old classification with the case that I'm focusing now in this slide, I mean, it can be really, at least this is my opinion, quite misleading because they are very different problems. If the number of towed cables is bigger than the number of freedoms, either in the suspended or in the not suspended configuration, the situation is still very different, because now the number of kinematic equation is more than sufficient to determine the end effector pose, because we have more equations than unknowns. And this means basically that it's not possible to govern a system of this kind simply by kinematic means, because we will never be able to establish so precise constraint that a bigger number of equations than the number of unknowns can be satisfied. So there will always be some cables that are slack and a smaller number of cables that will be towed. Statics, however, in this case is not sufficient to determine the cable tensions because we have more cable tensions than equations. And this is the classical problem of having infinite solutions for cable tension. So we have to find a convenient tension distribution in rigid body mechanics. But again, kinematics and statics are decoupled as they were before. So basically, this is just an explanation of the framework we've been considering so far. By the way, how long did I talk so far? Sorry,
it's been about 10 minutes or so, 10, 15 minutes.
10 minutes, okay. I wish to talk 15, so I have 5 more. Now, an underactuated CDPR is a CDPR that has fewer actuators than degrees of freedom of the platform, like in the picture that is shown here. Underactuation always implies that the end effector is under constraint, because of course, if we have less cables than degrees of freedom, even the towed cables will be smaller than the degrees of freedom. And this means that our end effector will always oscillate once the input variables are assigned, because there are some freedoms that are not saturated. And so pose depends on kinematics and mechanical equilibrium as well, as I mentioned before. Under constraints and underactuated, however, are 2 different concepts. Like, let's consider the picture at the left-hand side. We see that this is a sort of reconfigurable CDPR with 4 cables where the pulley connecting each cable to the frame can move on a slider. So basically, this means that we have 8 actuators. So of course, the system is over-actuated. We have more actuators than freedoms at the end effector. However, the system is still under constraint. Why? Let's go directly to the, well, if we try to solve the inverse problem, namely, if we completely assign the end effector pose and we ask the question, can we find some actuation variables so that both kinematic equations and equilibrium equations are satisfied? The number is yes, and there are infinite solutions. And now I don't want to focus on this because I have no time. However, once we try to solve the direct problem, namely we assign the input variables, our system still becomes a 4-cable under constraint robust, because the platform is suspended only by 4 cables, assuming they are all active and towed, and which means that it may still oscillate with 2 degrees of freedom. And so kinematics and statics are still coupled. I will skip this further example. So why are we interested in underactuated CDPR? Basically, I already answered to this question in my intervention before, because we see that probably the most, well, certainly the most used cable system in the world is the standard crane. which is a system with 3 actuators, but still with only 1 cable, which means that when the impulse will be assigned, the payload will be able to oscillate with 5 degrees of freedom, and will be able to control only one of the post variables of the payload. So we realized that since this is the most used system and most cable robots before Darwin and before Tobias and Stefan basically were mainly available in research labs, now things likely are changing for us. Probably we thought that there could be space for systems that were not as underactuated, as under constrained as a single crane, but perhaps showing not so many cables, mainly not all of them around the payload as in academic labs. For instance, they can be used for positioning tasks where the end effector oscillations need only to be mitigated rather than precisely controlled. Now, a little bit about modeling. I will be short on this because there's nothing really interested in these slides. This is just the fact that the kinematic constraints basically tell us that the vector going from the anchor point of the cable on the platform to the exit point of the cable from the frame is a vector that whatever the kinematic model of the system is will always depend on the platform pose zeta. And the kinematic constraints means setting that the magnitude, the square magnitude of this vector must be equal to the cable length, which is the parameter that basically you are able to control. And we have a number of, in an underactuated robot, we have a number of these constraints, which is smaller than 6, as I mentioned before, which means that if we want to try to find, to solve the kinematics, we have, as I already mentioned, fewer equations than post variables. This means that the kinematic problem admits infinite solutions, since the system still has some freedoms. On the contrary, when we introduce a static model, which is basically the equation where the cable tensions left multiplied by the transpose of the Jacobian is set equal to the external wrench applied on the platform, we will achieve the possibility to have a square system that will make a finite set of solutions. And this is what we call direct geometrical static problem. A few results. If we consider a system with 2 cables and we assume that they are all taut, we see that we have a fixed reference frame that we call XZ, a mobile coordinate frame that we call XY and ZY, and we can have 2 operation modes depending on the axis Y prime to be point in the same direction than Y or in the opposite direction than Y. And we proved that basically the geometrical static problems that I mentioned before admits 12 solutions in the complex field for each mode for a total of 24. 24 possible equilibrium configuration where the system can lie. However, not all of the solutions normally are real. In this example, only 12 are real. And not all of them admit positive tensions in cable. In this example, only 5 of them. Are these all feasible? Really not, because then we have considered stability. And if we consider stability in the plane, only 3 of the solutions are feasible. But if we let the possibility of our system also to go off the plane, because there's nothing that constrains the platform to remain in the monitor plane, actually the possible instability of the system increase, and actually we will have in this case a single pose that is real with positive cable tension and that is stable under any perturbance that it may suffer, which is the first one. This kind of reasoning, well, another thing that is interesting to observe that We also have to consider possible equilibrium configurations where a single cable is towed, because like in the picture that is shown here, we see that the assigned cable length of the first cable is bigger than the distance between A1 and B1. This means that this configuration is basically possible. So we not only have to consider the configurations where two cables are towed, but also we have to consider all the possible configurations where a single cable is towed and consider the possible stability of them. The reasoning apply also to situations with 3, 4 cables, 3, 4, 5 cables. We solved all these problems and we see that the number of possible solutions actually explodes. With 3 towed cables, the number of solutions of the direct static or geometrical static problems is 156. With 4 cables, the number of solutions in the complex field is 216. With 5 cables is 140. Clearly, not all of them will be real, not all of them will have positive tensions in cables, not all of them will be stable, but however, a number of them can be real and stable. And this means that basically with our control, if we simply control the cable length, we really don't know where the cable, and in which of this feasible configuration our platform may lie, because they will be characterized by the same cable lengths. And basically, this is everything that I want to say, and I'll leave the stage to Eduardo. I have no time to speak about the inverse problem. Eduardo, sorry for stealing you for minutes.
Not a problem. Okay, can you see my screen? Can you hear my voice?
Yep, it's good.
Okay, you should see my pointer as well. Okay, I'll start my part of the talk by talking about one other problem we investigated in these years, which is the one of static workspace characterization for this kind of underactivated robot. That is meaning basically, given another activated robot design, what can I safely do with it? Well, as for any cable robot, the workspace needs to be, of course, range feasible. That means the cable tension must stay between upper and lower bounds. And in addition, since I cannot control all the variables of my system, I have to restrict my analysis to some specific kind of workspace. And we saw that restricted the analysis to a reachable workspace, which is control the position of the platform and see if there is at least one attainable orientation for all the cable intention could be a good start point. So since our work showed that by slightly changing cable length from an equilibrium configuration, a cable might become slack, we investigated also how much given robot configuration was resilient to cable length changes. Or in reality, what we are interested in is resilience with respect to cable actuation errors. As more error in the cable length will result in a slack cable, the corresponding pose is not safely attainable. To study this phenomenon, we first needed to establish which robot variables might affect render vector pose change. Differential kinematics shows us that since the robot Jacobian is not full rank, meaning his rank is less than the number of degrees of freedom, an infinity of rigid body motion may happen for a given cable length velocity or cable length instantaneous change. If we partition the robot coordinates into controlled ones, which varies because of the cable length change, and free ones, which may vary regardless of the cable length change, we may analytically compute two special matrices, which are a right null space and a right inverse of the robot Jacobian, and express the end effector twist as a linear combination of the free and effector coordinates and the cable length changes. So by pre-multiplying statics by the right null space and inverse transpose, we can obtain two special equations. The first is a constraint that the end effector coordinate should satisfy when attaining static condition, and the second allow to compute cable tension for a given static configuration of the end effector. If the cable length changes quasi-statically, the differential analysis of the static constraint establishes the causes of the free coordinate variation due to cable length variation. In addition, we may also determine how cable static tension are affected by cable length changes, which was our objective to start with. Substituting the results of the first differentiation, which can be solved for the end effector, for the differential of the free coordinates of the end effector in the second one, we end up with a with this relation where we correlate the variation of the static cable tension, variation of the cable length, and the matrix correlating these changes as the units of a stiffness matrix. We thus propose the formulation of a new performance index called maximum tension variation under a unit cable displacement error, which characterizes each reachable configuration. This index is defined as the maximum infinity norm of the tension percent variation under a unitary cable length error. The tension percentage variation is obtained by pre-multiplying the tension variation by a diagonal matrix containing the reciprocal of the cable tension and by 100. The unitary cable length error infinity norm corresponds to a physically sound error model constraint, since it basically means that cable errors are between minus and plus 1, which is selected as an arbitrary constant. And the use of infinity norm on cable tension percentage variation allows to determine the maximum absolute value of this error. This is by definition, luckily for us, the infinity norm of the stiffness matrix we just introduced. Note please that the use of the tension percentage variation is justified by the fact that very small tension changes in an almost slack cable are as important as large changes in a well-taught cable. Then, by using this tension variation concept, we also proposed a new workspace definition, which we call the tension error insensitive, where cable tension maximum and minimum bounds were recomputed at each pose, depending on the expected maximum tension variation for each cable, thus restricting basically the range feasibility criteria, accounting for non-possible cable errors. In this picture, we are showing planar 2-cable robots and spatial 3-cable robots workspaces characterized by the performance index proposed in the slide before. And also we showed how this workspace varies if we account for non-cable error limits. For example, this is with no cable errors, this as well. And then we have 1 millimeters, 5 millimeters, and 1 centimeter error. We may see that the tension vary very much when cables are more horizontal and the effector is in the upper part of the workspace, which is colored red. And we also can see that these two architectures, 2-cable and 3-cable robots, are not very influenced from a range feasibility point of view by cable actuation errors, since the workspace size does not change. The story is unfortunately completely different for a generic 4-cable robot, which is in fact affected a lot by cable length error. And his tension insensitive workspace may be reduced up to 20% of the theoretically range feasible one, if we account for example, in this case, for a 1 centimeter error in each cable or 0 error in this case. Another possible application of the proposed performance index is the one of set point optimization. If, for example, we use a 4-cable robot for a positioning task, thus we have actually an overactuated system from a task perspective, its orientation can be optimized with respect to this index, so that natural cable length errors will minimally impact the end effector actual configuration from a range feasibility point of view. The optimization, of course, needs to be constrained by the fact that the attainable orientation must be static if we are looking for equilibrium position and needs to be branch feasible. And if the orientation is determined by minimizing or maximizing,
Unfortunately, it looks like we lost Eduardo. I guess
Yes,
we can.
I fear so.
Yeah, maybe we can give him a minute or two to try to join back in.
Okay, I'll try to write to him to let him know if it doesn't read Zoom.
Yeah, hopefully it was just an interruption in his network connection, and then he can just log back in, but we'll see.
And try also to call him on the phone. Okay, actually it seems that his computer decided to crash just now. So he rebooted the PC and he should be back with us soon.
Okay, sounds good. We'll give him a
But
couple
you
minutes.
can cut his presentation when it will be, when this time will be over. No problem with that.
Sorry, I didn't catch what you said. Can you say that again?
You can cut his presentation when his time will be over, in the sense that in any case, it's pretty much modular. There are several topics. We are not forced to go through all of them.
Okay. Thanks.
Thank you.
Oh, looks like he's back in.
Philip,
Yeah.
Philip, we may
Yeah.
stop recording and then resume the recording after Eduardo is back.
Well, I think he's back. I just gave him a co-host status, so.
Perfect. So there's no need then to do that.
Yeah, are you there, Eduardo? Seems as if he's here. If you are speaking, Eduardo, you are maybe muted.
Eduardo, if you can hear us, can you just write on the chat? Okay. We can't hear you. We can't see your screen. Your PC doesn't work. Okay, he decided it's very bad timing for your hardware to to leave you stranded. I don't know. Perhaps we can give the word to the next speaker and see if, in the meantime, Eduardo managed to have his PC back. I don't know.
Sure. I mean, we could maybe move on to questions, and if Marco, you want to pull up your slides again, we could just kind of see if anyone had any questions on the presentation before moving on.
Sure. Okay, I'm just okay. Any questions so far?
Well, I guess I actually had a question.
Please.
So I actually really liked this talk. It was actually very informative for me, since I've never really thought about this particular problem. I've always kind of thought of the over-constrained or redundantly constrained case. Do you think this is a case where additional sensor measurements would actually be very beneficial? Because you're kind of highlighting how just knowing the cable lengths isn't enough, right? And so you have to move on to the statics, which you can solve, but there are still challenges with that, right? So would there be benefits of having other sensors involved?
Oh, definitely, definitely. So actually, there can be several sensors that can be considered. The easiest and the cheapest one are probably sensors on the pulley that allows us to get extra information about the orientation of the final pulleys that guide cables into the workspace. They are probably the cheapest and the simplest to implement, but they are not the most robust, because in any case, the orientation of the pulley plane is not, I mean, there is really nothing that constrains the cable to remain on the pulley plane.
Mm-hmm.
Then you can measure, of course, the tension, as many of you do, which provides a very useful and another very useful information. But tension informations are not necessarily very clean, and also depends on which part of your system you implement your force sensors. Now we are actually exploring the possibility of having extra information directly in the Cartesian space, namely on the end effector. And this means using either IMU or vision systems or laser system, but we are mainly interested at the moment in IMU for several reasons.
Yeah, I mean, yeah, that makes a lot of sense. Yeah, and can you comment on how you would? So I think like the cable tensions, I think, you know, it's pretty straightforward how you'd embed that in your kind of in solving for the pose. But something like an IMU, can you comment on how you would actually go about integrating that into your method here?
Okay, actually the expert on this is Eduardo. Is Eduardo back? Just to answer this question.
Oh, right.
He wrote in the chat.
Can you hear me now?
Yes.
Yes, Eduardo.
Okay, I'm very sorry for that. Never happened before. Of course, it happened while I'm presenting. If I can answer your question about integration, basically we are looking for a commercial solution which would allow us to have a high sampling rate with a high accuracy of especially orientation angles. So we are looking about industrial dynamic inclinometers or even tactical grade ones.
Mm-hmm.
So depending on the need for accuracy, you can choose whether of the two options. For example, industrial may have a good enough accuracy if you just need to damp oscillation. If you really need to do fine control, probably tactical series.
Yeah, that makes sense. So you're kind of just kind of doing direct integration of the IMU measurements, and if you're talking about tactical, basically the bias and the noise is actually very small, and so you're not going to have a solution that drifts too much over short periods of time, right?
Of course, yes.
Okay. Oh no, that makes sense.
Okay, should I go on with my presentation?
Well, that's a good question. So, for following the original schedule, we only have 2 minutes.
Okay, maybe I just cut short with some conclusions about dynamics of the system and planning.
I think that'd be my recommendation. Maybe just if you can give like a 2 to 5 minute summary of just kind of yeah, just leave us in a good place that you're happy with in that time.
Okay, are you seeing my screen now?
Yes.
So skipping the modeling of things, basically there is one big issue when you are planning trajectories for underactivated cable robots, which is you cannot freely assign a trajectory, even if you account for the dynamics of the system. Because if you pre-multiply the dynamics for the right null space transpose, you end up with a sort of constraint on the end effector motion variables, which you need to satisfy, or your system won't answer the laws of rigid body mechanics. So basically, if you do planning, you should kind of account for this kind of internal dynamics constraint. So building upon that and actual other work we did to estimate what are the free motion frequencies that the platform may oscillate with, we end up actually with two kind of trajectory planners, which has different kind of characteristics. First kind of planner shapes a nominal trajectory and limits the oscillation of the platform while performing a trajectory, whereas another planner actually tries to completely eliminate these kind of oscillation while performing a trajectory, but needs to be solved offline. The first technique is built upon input shaping with a known frequency-based trajectory planning techniques. But if we know the natural oscillation frequency of the system, basically we can devise this shaper and convolute this function, which is the shaper, with an original path of our system. We can end up with a trajectory planner that helps the system minimizing oscillation both during the path and at the end of the trajectory. If instead we are interested in completely eliminating oscillation, we need to look at a more complex trajectory planning technique. For example, we developed this trajectory planner called rest-to-rest trajectory planning, which actually allows us to completely prescribe the geometric path of some coordinates we want to control and only modify the motion law with which we follow the path. And this is done basically by adding additional design parameters of our motion law, which are called K in this slide, and solving a boundary value problem in which the internal dynamics of the system is the differential equation, and the static constraints at the start and the end of the trajectories are the boundaries we need to satisfy. Basically, this allows us, this trajectory is one which kappa was equal to 0, so was not planned according to the rest trajectory planning method. And you can see that just the inertial action on the platform excite the oscillation we were talking about in the beginning of our talk. Whereas if we use the rest trajectory planning, oscillation are eliminated, or of course, the system is real, can slightly oscillate because, for example, because of actual vibration we did not model. But oscillations are incredibly low. So this kind of wrap up my talk. I'm very sorry for the technical inconvenience. I was hoping from home I won't have any, but this happened. I'm very sorry for that.
All right. Well, thank you, Eduardo. I say we do have maybe a time for one quick question, if there's anything the audience would like to ask. Well, then maybe I'll just comment that those videos were very convincing at the end, and definitely, yeah. I mean, even in the real world case, I mean, those oscillations were very minimal. So I think that was very impressive to see.
Thank you very much.
All right. Well, then I'd like to thank you, Eduardo and Marco, for your great collaborative presentation there. And I think we'll move on to our second speaker for the session, which is Mohammad Khosravi, who will be giving a presentation titled Cable-Driven Parallel Robots, Control Challenges and Solutions. And I can see your screen, so that is a good start.
Do you hear me?
I can hear you, yep.
Hello, everyone. First of all, let me thank you all for your presence. This presentation addresses the control challenge in CDPRs and discuss some approach that can be employed suitably in cable-driven parallel robots. It's notable that our presentation focus on fully constrained cable-driven parallel robots. First of all, let me break down this area into following fields. In introduction, I would like to give you an overview on excuse me, features and challenges in fully constrained cable-driven robots. And next, in dynamic section, we focus on dynamic analysis of fully constrained cable-driven robots, and several modeling types that have been developed in literature are introduced. In the control section, we classified the control algorithm which have been used for fully constrained cable robots into two categories: knowledge space-based control and NDO-based control. In knowledge space-based control algorithm, internal force concept is used to ensure that all cables are in tension. But in NDO-based control, which is developed recently in our group team, and NDO, nonlinear disturbance observer, is used to satisfy tensionability condition in fully constrained cable-driven robots. As we know, to cope with parallel robots drawbacks from 4 decades ago, a new attitude formed in robotic society. This attitude is based on replace linear actuators with active cables, and based on this fact, cable-driven robots are introduced. Replacing rigid links by the cable enables cable-driven robots to use in many high speed and large applications similar to RoboCrane, SkyCam simulator, and large radio telescope. However, using the cable instead of rigid links leads to some challenge in design of CDPRs. Unlike the rigid links, cables can only apply tensile forces, and therefore they should be kept in tension in the whole workspace of the robot. Based on the satisfaction of tensionability condition, CDPRs are classified into under constrained and fully constrained CDPRs. Regarding to this condition, Several types of workspace have been defined for CDPRs, such as control level workspace, branch feasible workspace, dynamic workspace, and so on. From kinematics viewpoint, similar to conventional power robots, inverse kinematics problem is straightforward and simple to solve, while the solution of forward kinematics is a challenging problem. And it should be noted that when we consider the elasticity of the cables, the kinematic problem is more challenging than usual. In this presentation, two major challenges in CDPRs are considered. Among the CDPR challenge, dynamics and control, in my opinion, are crucial ones. As we know, for accurate and higher speed application, dynamics of cable must be considered in dynamic analysis and control of such robot as well. Furthermore, in order to avoid structural failures, control algorithm should be designed such that all cable remain under tension in all configurations. As we know, dynamic behavior of cable is one of the major challenges in mechanical design and control of such robots. Cable can be modeled as elastic elements and may encounter elongation of vibration. This problem is a critical concern in applications where high bandwidth or high stiffness is a stringent requirement. It should be noted that exact modeling of cable dynamic characteristic is very challenging problem and very complicated. Because of this, in many research, based on application, dominant dynamics of the cable is considered. It's worthy to note that the obtained model not only should be accurate sufficiently, but also this model should be used in control algorithm. Because of this, dominant dynamics of cable is considered in many applications. Based on this fact, different types of cable modeling have been used in literature. The simplest one is ideal model. In this model, cables are modeled as massless in elastic string. This model has been widely used in literature in control, especially in control. When the mass of end effector is greater than the cable's mass, the dominant dynamics of cables can be considered with elasticity of the cable. Based on this fact, in elastic massless model, only the elasticity of the cable is considered. And in a static application, continuous model with mass and elasticity is considered. And furthermore, Kelvin-Voigt approach has been used in modeling of the cables. In this model, cable is modeled with lump mass with elasticity. It should be noted that when we use ideal model for the cable, end effector dynamics with positive tension can be given as the first equation. And if we combine the actuator dynamics, we reach to total dynamics with positive tension for the cable robot. But it should be noted that ignoring the elasticity of the cable in our analysis may lead to unwanted vibration in the end effector. This situation is very harmful when the application needs high speed or high stiffness. Because of this, we should include the elasticity of cable in our in dynamic analysis of fully constant CDPR. When the elasticity in the cable is considered, actuator position is not directly related to the end effector position. And in this situation, both the cable lengths before tension and the cable lengths after tension may be used as independent variable in order to analyze the dynamics of the manipulators. Based on this fact and previous researchers that mentioned that the axial elasticity is dominant in comparison to transversal vibration, elastic massless cable model can be estimated by an axial spring. With this assumption that cable model as a linear spring, we can use Euler-Lagrange formulation, the potential energy, kinetic energy, and using, as I said, using Euler-Lagrange formulation, the equations of motion can be obtained as follows. These equations represent cable-driven robot as a nonlinear and coupled system. It's worthy to note that these equations are formed in a two space, in task space and in the cable length space, and these equations are related to each other from Jacobian transpose. These equations can be transformed to a standard model of singular perturbation theory, and based on singular perturbation theory, we can design appropriate control to reduce the vibration of this system. But let me come back to the control of CDPRs with positive tension. As we know, in order to avoid structural failures, control algorithms should be designed such that all cables remains in tension in all configuration. While designing a controller in task space, the control action can be either positive or negative, which is to be mapped to the cable space with an optimization algorithm to find the actuator effects. Because of this fact, based on this fact, CDPR's control algorithms are equipped with an optimization algorithm to find the positive cable forces for a given F. As we know, the available methods for positive tension distribution of the cables in CDPRs are formulated using null space of the Jacobian transpose. And the algorithm based, the control based on null space is formulated as follows. As you see, tau is obtained based on pseudo inverse of the task space range plus internal force, which internal force has not any effect on the end effector position. To have a better judgment about null space-based method, I show you the results of robust PID control in combination with internal force for cable-driven robots. As you see, when the desired position are constant, this controller, robust PID control, in combination with internal force, has a good performance. In another scenario, for a circular trajectory, desired trajectory, this controller has average performance in tracking. And to study the repeatability of the robot, another test was performed. And as you see, for lower speed of the end effector, the repeatability of the robot is good. But when we increase the speed of the robot, as you see, the repeatability is poor. And in my opinion, the source of the errors may be the neglecting the elasticity of the cable in control design. And furthermore, because this algorithm is based on null space of Jacobian transpose, it's very sensitive to the kinematic uncertainty. Keep in mind that iterative nature of the null space-based algorithm limit their application in real-time scenarios. Furthermore, as I said before, as most of the optimization algorithms are iterative, they may not satisfy the real-time computing requirement. In addition, the kinematic uncertainties affecting the Jacobian result in extra error in the calculation of positive tension distribution. One approach that we recently worked on it is control-based force distribution. The idea is, from the control perspective, the positive tension in the cables can be interpreted as using a saturation type function with predefined positive lower and upper bounds right before applying the control effort to the robot. With this situation, saturation type function work as a big disturbance on the system and may affect the tracking performance of the robot. Because of this, in our purpose control-based force distribution, we estimate the effects of this disturbance, and then we compensate it with our controller. The estimation of the effects of saturation type function is performed by nonlinear disturbance observer. As you see, this control algorithm is independent from null space of the Jacobian. And in this slide, you see the observer dynamics, and the hour disturbance, which is estimated by the observer dynamics. And as I said before, we compensate the effects of saturation type function with an observer, estimate with an observer, and then in control design we use this estimation. In this presentation, we use a sliding mode controller as a controller in combination with proposed control-based tension distribution. To show the effectiveness of the proposed control algorithm, a simulation study has performed on a special cable-driven robots with 8 cables. And as you see, the results in comparison to null space-based method are very better, very better. And in this slide, you can compare the control effort with internal force based method and with control based force distribution method. As you see in proposed approach, the magnitude of the cable force is lower than internal force approach. In another simulation, to have a better judgment, we use a periodic desired trajectory, and as you see, the errors are very small. And furthermore, the cable forces are positive in all workspace of the robots. In this slide, I show you the preliminary results of experimental results on a planar cable-driven robot, and the results show that nonlinear disturbance of the base method is have greater tracking performance in comparison to null space-based methods. If I want to summarize the advantages of proposed control-based force distribution, which is introduced in this presentation, I should say that the iterative optimization procedure for PTD computation, which is generally formulated based on Jacobian, is replaced by the control-based method. And furthermore, improving the PTD computation time, which is important for the real-time control of CDPR, is another advantage of this method. Thank you very much. And I open to your question.
Thank you very much, Mohammed. We do have time for some questions from the audience. Any questions? Oh, Hamid. I'll let you go first, Hamid. I think you got in there first before.
I'm sorry, Tobias, but I have a very quick question, Mohammed. It is very interesting to see that we don't need any Jacobian or Jacobian transport or null space to do the tension, to keep the cable tension. But can you give us some the philosophy of that? It seems that it is not neglected or completely deleted from the problem, but it is somehow embedded in the control structure. I would like to have your comment on that.
Thank you. A good question. As I said before, in this control scheme, we estimate the effect of a saturation type function, and then we compensated through our controller. Yes, and if you see this equation, our disturbance, which is showed with d total. Yes, d total is directly used in our controller. Yes, and because of this, we don't need to null space of the Jacobian. We can control the system.
Thank you.
Tobias, you have a question?
Yes, thanks for the nice presentation. I have a question regarding the influence of the cable, because, well, up to now, most of us, if not all, are mainly focusing on, say, applications where the cables are more or less straight lines. Yeah. Now, if
Yes.
we really go beyond this, and I have talked to some engineers, if, I mean, applications say around 100 meters workspace diameter would be possible, the cables cannot be treated as straight lines anymore, and we would have some chain model to be applied. Are you aware of real-time control approaches or even concepts that would allow for that case?
Very nice question. As I said before, there are many models for the cable based on the application. We developed massless elastic model for the cable, and as you see, this model can be transformed to singular perturbation theory. Using singular perturbation theory, you can control fast dynamics of the system and slow dynamics of the system separately. Yes, and based on this fact, you can reduce the effect of vibration on the end effector.
Thank you.
Welcome.
Yes, but I guess still neglecting the mass for very long cable is not a very good assumption. And this brought a very large difficulty for the control, since the modeling and incorporating the modeling into the control is very difficult. I guess this is one of the open questions or open
Yes.
research problems that shall be addressed.
Any other questions from the audience? I have one quick question. So I really like the idea here of using the disturbance observer to essentially estimate all these errors in your dynamics, and then you take advantage of this estimate to improve your control, and ultimately, you know, avoid keep all the tensions positive. I was wondering, either through the theory or experience, do you see any issues or need for certain types of excitation in the dynamics to be able to estimate those parameters? So like in adaptive control, we typically have this persistence of excitation conditions where we have to have kind of things changing to be able to actually, you know, converge our estimates of the parameters. Is that something that you see here?
Yes. As you said, we have some constraint in this control, which is under investigation. The movement of the robot should be in range closure workspace. Yes. Mm-hmm. If the movement of robot is out of the workspace, controller workspace, or range workspace of the robot, this control algorithm will be failed. Yes.
Sure. Okay. I mean, so that makes sense to me. I was wondering if, though, so for example, if you just commanded very simple motions that weren't very dynamic, would you be able to actually estimate all the parameters you need to be able to converge your estimates there?
The convergence of a nonlinear disturbance observer is necessary, and the speed of the convergence of or NDO should be greater than the bandwidth of the control loop. Yes.
Yeah. Okay. Yeah, that makes sense.
Thank you.
All right. Thanks. Well, thank you for your presentation, Mohamed. We'll move on to the third presentation in the session, which will be given by Dominic Martinez on automatic tracking of free-flying insects using a cable-driven robot, with a presentation titled "The Analogy Between Cable Robots and Robotic Hands."
Thank you, Ryan. Give me just a second. Do you see my screen now?
Not yet.
Not yet. Wait a second. Is that better?
That looks good.
Okay.
Perfect.
Okay. So good day, everyone. Good evening, or in Iran, I guess. So I'm gonna talk to you about the dimensional synthesis of cable robots. The title written on the program, I think, is not the correct one because I changed my mind and forgot to update it. After all, I was one of the co-organizers, so I could have thought about it. So why talk about the synthesis problem? I think we mentioned in previous talks that one of the key advantages of cable robots is that they are capable of redeploying or reconfiguring quickly. So choosing quickly the right geometry would be critical in that case. And also, I think it could be useful to improve on architectures that we know, like Kojiro or the Ipanema or the cable robots that we've seen in the literature before. Could we get a few more improvements on those by really using an optimization, a formal optimization procedure? So, so that's what I have in mind. And I started working on this maybe 10 years ago. And I've been working on it on and off. And so the problem, if I state it formally, let's say I have my cable robot with the cables in red, and I have my my anchor point position would be AI, and on the fixed frame, and the attachment point on the end effector would be given by vector BI with respect to another reference point on the end effector, and the position of that reference point on the end effector would be P with respect to some fixed origin O. Okay, so I'm trying to find the AIs and BIs that define the geometry of my cable robot, basically. When I started working on this, we started from the wrench closure workspace condition. Those who are familiar with cable robots know this condition. So basically it states that we can balance any external wrench on the end effector if I can find a vector of tensions, T, in the null space of the Jacobian matrix that is strictly positive. And I shouldn't have the equal there, it should be strictly positive. And so what we did from there, we looked at the alternative formulation of that. There's a theorem that says that if you can find for a given position of your cable robot or of your end effector, if you can find a vector lambda that satisfies all these other conditions there, then that means you're outside the range closure workspace. So that means it's either condition 1 is satisfied or condition 2 is satisfied, but not both at the same time. They can never be satisfied at the same time. So we started from this alternative formulation, this dual formulation, and we relaxed it in the sense that we linearized it over a box by relaxing the constraints, because those are nonlinear constraints if you consider that P is a variable that can vary inside the box in the workspace. So your matrix W depends on P, and then you have a vector P, for example, that multiplies lambda, so it's nonlinear. And so we relaxed it and turned it into a linear problem. So we kind of, while doing that, we kind of overestimated the opposite of the workspace, so the complement of the workspace. And that means we underestimate the workspace in some sense of the cable robot. And then we took the dual of that, and this gave us a set of conditions that are linear, and when they are satisfied, you're sure that the box over which you relaxed is inside the workspace of the cable robot. So, but you're still underestimating the workspace. So graphically, what this gives is, if you take a bunch of boxes, this is for a planar cable robot, you have your X, Y axes, and you have the orientation, the other axis, which is the orientation of the end effector. So if you verify this fourth condition for all these boxes and keep only those which satisfy the condition, then you're going to get a subset of the workspace, basically. You're going to underestimate the workspace. So our idea was to use these conditions to do the optimization. So now, from now, we let the geometry of the cable robot, which is embedded in this matrix RJ, we let it be a variable. And so we optimized while ensuring that all these boxes remain in the range closure workspace, because we needed to satisfy all these conditions there. So that's what we did. And we tried some randomly generated geometries of cable robot. And this is one example we got with 4 cables for a planar cable robot. We have 27 boxes there because it's 3 by 3 by 3. And we get this type of nonlinear program, which we need to solve. And we worked on the scale of those boxes. We maximized the scale S of the boxes in this problem. And we ended up with this strange, but if you think about it, a bit logical geometry for a cable robot. Okay, so that was planar, and we were fairly satisfied with it, although we didn't get, I would say, revolutionary geometries. So we tried to move to spatial cable robots from there, and the process is fairly similar, but it's a lot more variables, a lot more equations, a lot more constraints when you're dealing with spatial cable robots. So this is one of the randomly generated geometries that we got for a 7 cable robot. And we started from our initial guess had the pink box was the maximum box that it could contain in its range closure workspace. And the largest box, the final box we got is the yellow one. So we were able to increase a little bit the range closure workspace. But this came at a very high cost. It took several hours to get a solution because we had several hundred constraints and hundreds of variables in this nonlinear program. So more recently, we gave it another try, and we decided to backtrack because the complexity of our problem was getting out of hand, and also because We didn't consider cable collisions in the previous formulation. We only had the wrench closure workspace condition there. So instead of guaranteeing that full boxes were included in the wrench closure workspace, we decided to use control points. So verify that a discrete number of points were included in the workspace. And we verified collisions between the cables by defining an ellipsoid. So the ellipsoid is the volume that we aim at. It's our prescribed workspace. And the black points at the surface of the ellipsoid are our control points for wrench feasibility. And to verify that we have no cable-cable collisions, we verified the intersection between the ellipsoid and the cable-cable collision regions. So what are those regions? These came from a previous paper we wrote. So we were able to obtain this quite simple expression of the region of cable-cable collision in the workspace of the robot. So this is for a constant orientation of the robot. As it moves in the workspace, you can show that the regions of where pairs of cable collide, they look like sectors of plane in space. And those sectors of planes continue at infinity. They have one apex or vertex here, and they are kind of flat cones that go on until without bound. And so if you trace several of them for different orientations of the same robot, this gives this kind of graph with parcels of planes everywhere in space. And you want to avoid those patches because you know that two cables are going to collide. Or in this case, in fact, the green regions are the ones where two cables will collide, and the blue ones are the regions where a cable will collide with an edge of the end effector. So, so basically, what's interesting about this shape is that it's convex, and our ellipsoid is convex as well. So their intersection is convex, and we can get well-defined inequalities that will make sure we do not have this intersection, basically, because everything is convex. So we can turn this into an infeasibility problem that guarantees that as we search for cable robots, we will not have any cable collisions inside our ellipsoid. So the final shape of the optimization problem is like this. So I don't want you to understand everything that's in there, but the conditions to avoid cable collisions are the inequalities right here. So basically, we tried to solve this for an example problem, and this is not published yet. We hope to publish it soon. So we went to design a CDPR to work inside an MRI. Why? This is a bit of a strange problem because you don't have much space inside an MRI to fit a cable robot. But our idea was to be able to drive a surgeon's tool by having the motors remotely placed remotely outside far from the MRI, so that they don't perturb the magnetic field, and so that the MRI doesn't affect the motors either. So so that was our main motivation. So we took the dimensions of an MRI and we set up a prescribed workspace, which is the box in red there, and the patient would be in blue there. And we generated randomly many cable robot geometries. Some of them, the problem was too large and we didn't even get convergence. But for some others, we did get a result. And our best randomly generated result was trial number 64. And as you see there, the time is in seconds. It was so it was several hours. I think that must be 5 hours approximately. And we got 98% of the volume that we wanted to reach. The 100th iteration is because we were too disappointed that we didn't reach 100% of the volume we had prescribed. So Simon, the student who worked on that, he set up his own design, and he used it as an initial guess, and he was able to beat his previous randomly generated guesses, but still the algorithm improved on his initial guess. So we were able to still to get to get some something useful out of the algorithm, although it was not purely random. And so that's the type of convergence that we got. And those are trials 64 and 100. So that's the initial geometry for the trial 64 and the final geometry for the cable robot. So you see that it automatically puts the points, the fixed points as far away as possible given the constraints. And it also moves the attachment points on the end effector. They're quite different in the final geometry from the initial geometry. This is our this is the initial guess that Simon entered by himself, by his own intuition. And the algorithm adjusted some positions to improve, but still kept the same overall shape, but still tweaked a little bit the dimensions to improve the final result. So that's what I wanted to cover today for the synthesis. That's where we are today, and we will keep working on this. Maybe, I don't know if I have some time, Ryan, I would have shown a few other videos of what we've been working on in the lab, or?
I mean, it looks like we have 13 minutes or so,
Okay.
so I'd say
Okay.
go ahead.
So I'm well within the time, thanks. So we've been working on a project on haptics and to use a cable robot in rehabilitation, physical rehabilitation. So we've put a cable robot inside a cave environment, and we've played our second iteration of the cable robot was to be able to play a Pong game inside that environment, and the paddle that you see is not real. It's projected on the walls, and as the user feels as the user hits the ball, he feels the weight of the ball in the inner. So we were able to apply a force that was quite realistic. If you played ping pong with a steel ball, or it would have been realistic. So, and then we went to another. So that's our third iteration, and it was tested on some real patients. They had to do a rehabilitation task, which was to move a box in a shelf, and so the cables applied forces to make you feel the contact between the cable, the box and the table, and also feel the weight of the box, of course. So that was published in a rehabilitation journal last year. And we've been working also on window washing. I know I think it was Darwin this morning who showed a robot for window washing application. Here, we have a bit of a different philosophy though, because we have only, I think we have 4 actuators in this. So, and we have, it's an under constrained robot because we only have 2 cables that suspend the end effector, and the end effector controls the pressure of the squeegee on the window by extending an arm and leaning literally on the window. And it does work. We've been able to clean some windows, and they look really clean once it's done. And this is this is a project by a master student who finished this spring, and she did basically a retractable column, or a retractable beam, I should say, because this one, there are other retractable columns that exist in industry. But what Clémence did there is it's a beam that's able to sustain some bending, which is not always the case when you see retractable beams like that. Sometimes they act like column, and they have to be kept vertical. This was what we did, and it goes with what Ryan, you were saying about exporting cable robots to make them useful for space applications. This could be a potential application for this. Okay, so I guess that will be all for me. Thank you for your attention.
All right, well, thank you, Philippe. We do have time for questions, so any questions from the audience? Well, then I'll jump in with a question.
Okay.
So, or questions, I don't know, we'll see. I was very interested in the convex optimization stuff you showed for the synthesis. So one thing that I didn't quite grasp was the wrench feasible equation. So that is a nonlinear equation in terms of the design parameters, right?
Which one?
That's a good question. I guess I'm trying to understand which one. So at the end of the day, you're using the 4th one, right? The dual of the relaxed.
Yes, yes.
So.
But at this point, once you're relaxed, you're linear, because
Okay,
it's a linear relaxation.
Okay. So that is then a linear equality and inequality constraint, right?
Mm-hmm.
And then can you go to the actual, like, one of the synthesis algorithm, or like the actual optimization problem? So I guess I was trying to understand. So is this does this just end up being like a linear program?
This is still linear, because I'm still considering I'm gonna have different RJ matrices for different boxes, but they're gonna be computed as distinct constants. So it's still linear there. But then if I let AI and BI, my synthesis parameters, if I let them to be variables, then it's nonlinear.
And so, yeah, that's what I was trying to identify where the nonlinearity shows up. Is it that scaling S, or is it elsewhere?
It is, because no, sorry. Yes, it's in the scaling, because there I'm trying to scale up my boxes. So P overlined and P underlined are variables. Sorry, P overline prime is a variable, and P underline prime is also a variable. But my P overline not prime is a constant, because I'm starting from a known box. So this is my known box, and this is my scaled box. So that's still linear here, but the nonlinearity is in RJ, because RJ, I didn't put the full explanations, but RJ is dependent on AI, and so it's a complicated matrix that's nonlinear.
Okay, so so that dual of the non-membership equation, so that ends up being the tricky constraint that kind of makes this actually complicated, right?
Yeah.
Okay.
Yeah. And I had to go through those 4 steps because if I went directly from 1 to 4, I could have said, okay, I'm going to relax the wrench closure workspace and get a linear relaxed membership constraint, but then I would have overestimated my workspace because I'm relaxing my constraint that I want to be feasible. So in order to underestimate, I had to flip it and flip it back again.
Yeah, no, that totally makes sense. Okay, cool. Now I understand where the nonlinearities pop up. Okay.
Thanks for the question, though.
Yeah, no, and thanks for the explanation. Any questions from the audience? Then I will add one more.
Go ahead, Ryan.
So again, I really like this idea. Is there ways to weight how much you care about increasing the the workspace in terms of translation versus rotation? Is that something you could encode in this problem depending on what you care for a given application?
Absolutely, absolutely. That would be very easy. You could just add a weighting matrix, and that would do it, I'm sure. Here we started with, for example, in this problem, we started with an ellipsoid that had already the right aspect ratio for our workspace that we wanted.
Mm-hmm.
But you could totally do it if you wanted to change the aspect ratio on the fly as you optimize.
Mm-hmm, mm-hmm. Yeah, no, I mean, again, I say it because like I would assume typically there's going to be trade-offs, right? Like if I want to increase the maybe the range of attitude that I can get with the end effector, I may have to trade off some translational workspace. And so I mean, it sounds like you're not kind of worrying about anything like that at this point, right? But you probably could embed something like that.
Yeah, I don't see anything that could prevent you from doing it.
Okay.
Yeah.
Interesting. I mean, and again, the reason I'm bringing this up is just because obviously based on experience, attitude tends to be very tough to get much out of. Whereas,
Yes.
Translation is kind of the great feature of CDPRs is that you can have
Yeah.
very, very large workspace, but attitude is always very tricky. And
Yeah.
I find that's always the part where you kind of just have to rely on intuition and look at previous designs and kind of guess. And so if there was a systematic way to say, okay, I really want to build up, this many degrees of yaw into like my attitude workspace, building that into the synthesis, I would see that be really interesting.
Yeah, I think so. And in fact, with Amid, we've been collaborating on cable loops because we thought that we saw that this problem of large workspace in orientation was a real problem. So we worked on a way around, if you want, because we didn't get what we wanted from traditional architectures.
Yeah, no, that makes sense. All right, well, thank you.
Okay, thanks, Ryan.
Well, I think that might be it for questions. So thank you, Philip.
Thanks again.
I don't know if you or Hamid want to have any closing remarks.
Yes, go ahead, Philip.
No,
any closing
I'll
remarks?
let you do that.
Yes, I would like, first of all, I would like to thank Ryan, Philip, and all our speakers that have spent very, very wonderful time with them. These 6 hours or or more or less 6 hours was very, very a good part of my life. And also I would like to thank all the audience who followed us very patiently. I would like to just give 2 short notice about our program tomorrow, if you don't mind, if I just give 2 minutes, not more than that for sure. We have from tomorrow, from early tomorrow Tehran time, the main program of the the RSI International Conference on Robotic and Mechatronic, ICRoM, will start. And I just want to show you the figures that have accepted our invitation, our honorable guests and the keynote speakers in 4 different areas of robotic. So please feel free to join us anytime tomorrow or on Friday. And that's all. I would like to thank everybody and hope to have you all sometimes after the coronavirus in Tehran, being your host and meeting you in person, one by one in Tehran, hopefully. Thank you very much.
Bye-bye, everyone. It was nice seeing you.
All right.
Thank you for organizing all this.
Thanks, Ryan, for coming.
Thank you. Bye-bye.
Thank you, everyone. Bye.
Bye-bye, Eduardo.
Okay, Philip, just a final notice. If you could send me the link of the recorded clip that we can use it maybe later on the website. And thank you for all the help and assistance you have given us.
Okay, thanks for the opportunity. See you.
See you. Bye.